Welcome everyone. We will start today the third day of the School of Electrochemistry. Thank you for everyone that is watching on the Zoom room and in the YouTube. We arrived yesterday 100 views in the YouTube. Thank you very much for all the attendance here and the attendance here in the Zoom room. And it's a great pleasure to me today to introduce our speaker, our first speaker of the day, Professor Mauro Bertotti. Is a good friend that I had and my old supervisor. I would like to introduce first here Professor Mauro Bertotti. Professor Mauro Bertotti received his bachelor from the Institute of Chemistry of the University of São Paulo in 1983 and became a postgraduate student at the same institution, where he received his master and his PhD under the supervisor of the Professor Roberto Tocoro. From the year of 1995-1996, he has a postdoc fellow in the group of Professor Derek Fletcher at the University of Southampton, UK, when he met Denuault, that will be our next speaker. At the University of São Paulo, he has remained through his career, where he was appointed as full professor in 2008. From March 2014 and 2018, he has the head of the department of the Institute of Chemistry. His research interests are electrochemical sensors, microelectrodes, and scanning electrochemical microscopy. He published more than 155 papers with almost 3,000 citations. Mauro loves to interact with the students and mainly the participants that would like to do questions. Mauro normally do questions during the presentation. Raise your hand, I will open your mic, or try to interact by chat as normally. And one of the phrases from Mauro always stimulates students, as I mentioned, to exercise considerable creativity and freedom during these years. Thank you, Mauro, to be here with us today. And if you'd like to open your camera and start to share your screen, it's with you today.
Thank you, Thiago. Good morning, good afternoon to everyone. Thiago, can I share my screen?
Yes, you could start now. Now put your full mode.
Is it working?
Not now. Try to share the full screen as we made previously. Perfect. Now it's okay. Now it's with you, Mauro. If you need some help, I will be here and I will manage the chat.
Okay. Thank you, Thiago, again. This talk is not going to be a seminar. It's going to be a lecture. So please try to interact with me, please. That's my ask for all you. So the idea here is to talk about cyclic voltammetry. My name is Mauro, and if I have time, I'm going to show you some examples of reaction mechanisms. Again, please try to interrupt me at any time, or by chat, or asking Thiago to talk to me. So I have divided this lecture in a few main sections. First, I'm going to talk about cyclic voltammetry. Then, how can I get voltammograms with microelectrodes and rotating disk and rotating ring disk voltammetry? And then, if possible, I'll show some examples of how can I get information from an electroreaction by using CV. If I have time, I'm going to use some examples. So, if I have an electrode process, for instance, a reduction, I have a species in solution. Let's call it as A. Here is the electrode. Here's the solution, if I change the potential of the electrode, if I made the potential more negative, then electrons can go from the electrode to the species. I have a reduction process. The important thing here, remember, I'm going to talk about this later. When the electrode is polarized, a thin layer of solution is going to be affected by the electron transfer process. This layer is called diffusion layer. Its dimensions are micrometer. I'm going to talk about this later. If I have an oxidation process, in this case, when the electrode is made more positive, electrons can jump from the species in solution to the electrode. In this case, you have an oxidation process. So in cyclic voltammetry, what we do is to change the potential of the electrode from a fixed potential, initial potential, to a final potential. You can do that by changing the scan rate. Go forward at a certain scan rate, then you come back. In this case, you have a waveform. I'm going to show you what is a waveform. It's a kind of triangle. In the reverse scan, you can probe the product electrogenerated in the forward scan. So by using cyclic voltammetry, you can get information on the thermodynamics of a redox process, the kinetics, and of the electron transfer process and the kinetics of coupled reactions. This is a typical waveform. You can start from initial potential at a certain scan rate, then you reverse the potential to a final potential. You can do that many times. This is a typical cyclic voltammetry. The shape is something like that for a reversible process. There are some important parameters here. I'm going to talk about them in a few minutes. So the important parameters are the initial potential, the final potential. You have to remember that the solvent is very important, and the electrode material is also very important. For instance, if you have mercury, you cannot work with mercury at very positive potentials because mercury is going to be oxidized. So you change the potential at a certain scan rate, and the scan rate can change. You can use very slow potential, scan rate potentials from, for instance, 1 millivolt per second to very fast scan rates. You can work 1,000 of volts per second. But a typical cyclic voltammogram is recorded using, for instance, 10, 50, or 100 millivolts per second. So a typical CV is recorded in 1 minute time. When you work with cyclic voltammetry, I think you remember that you measure current. And current depends on 3 main modes of transport. The first one is migration. I think you know you have also convection and diffusion. We always try to eliminate migration and diffusion and convection. The idea is that the transport of the electroactive species to the electrode surface is done only by diffusion. So we can eliminate migration using a supporting electrolyte. It can be an inert salt like potassium nitrate, sodium sulfate, sodium perchlorate, and organic salt. And the idea is to eliminate migration. let me now show a table here. You can see a table. It shows limiting currents for reduction of lead at different concentrations of supporting electrolytes. So now I want to interact with you. The question is, how can we explain these results shown in this table? Who can help me?
Mauro, until someone could help you, there is a question here in the chat.
Yes, please.
Nazim is requesting, probably you will talk about this, but the question is in the direction and how would be plot if you have a irreversible process, because we are talking about now.
I'm going to talk this later.
Perfect. Now you could try to interact, and I will check if someone will raise their hand to try to talk with you.
Yes. So the question is, how can you explain these results? Who can help me? Why I can see a change in the limiting current by increasing the concentration of the supporting electrolytes. Who can help me?
Rona mentioned in the chat,
please.
There are more ions at higher concentrations.
Yes, that's true. If you have more potassium and nitrate ions in solution, you can say that the transport number is the fraction of the total current carried by lead ions. It decreases if you have more potassium nitrate in solution. So you can see here that when there is no supporting electrolyte, the current is very high because the transport is done by diffusion and migration. When you start to increase the concentration of supporting electrolyte, you can see that the current decreases. If you have 100 more supporting electrolyte in comparison to the electroactive species, in this case lead, is almost 1 millimolar, then you can see that the current is not changing anymore. So the idea is to always add a supporting electrolyte at a very high concentration, 100 more in comparison to the electroactive species. In this case, migration does not influence the current, and the transport is only by diffusion. Convection is also important. So if there is no steering, there is no convection, and then the material is transported to the electrode only by diffusion. In this case, there is a very important equation in cyclic voltammetry, is the Handler-Savage equation that can predict current as a function of some parameters: area, electrode area, concentration, diffusion coefficient, and the scan rate. So the idea is always to add a supporting electrolyte, very concentrated, and no steering. At these conditions, the material arrives to the electrode only by diffusion. This is a simple configuration. Is an electrochemical cell. You have a reference electrodes. I'm going to talk about them later. A working electrode and the auxiliary electrode. The auxiliary is generally platinum wire. So when you apply a potential to the electrochemical cell, for instance, if you have ferricyanide, is an electroactive species, because it's a probe. The behavior is very well known. It's a reversible probe in supporting electrolyte. You can see that at a certain potential, ferricyanide is going to be reduced. Again, this happens in a very thin layer. The dimension is micrometer. It's the diffusion layer. So let me ask a question again. What's the amount of material that's consumed during a forward scan? Do you have an idea? It's a lot or is negligible? Thiago, I'm asking them again.
Oh, yes, I am checking the chat.
Please.
And the hands I am checking too. No hands and nothing in the chat.
Yes, I'm sure they know. Someone knows that.
Yeah.
How much material is going to be consumed during a forward scan? Remember, only the material that is in the diffusion layer is going to interact with the electrode surface.
We
Is
have
there any answer?
we have 3, 4 now. Primaggio say a lot because that's already at the electrode. Negligible,
Yes.
a lot,
Yes.
and
A lot.
little. Otherwise, we will be in the mass transport limit region. And Paul Newman, less material. Andrea, less negligible compared to the bulk concentration. And GL say negligible.
Okay. Yeah, that's if the solution is stationary, so there is no convection, only the material that's very close to the electrode surface is going to be affected by the potential. So the amount of material that's going to be, in this case, reduced is almost zero. So the bulk solution is not affected by the change in the electrode potential. So the amount of material is almost zero. That's going to be reduced in this forward scan. So if you see here an electrode picture, here is the electrode, here is the diffusion layer, and here is the bulk. The double layer is this interfacial region. It's a very, very thin layer, is angstroms. The diffusion layer is the part of the solution that's close to the electrode surface, and this layer has a composition that's going to be changed. It's affected by the electrode reaction. And the bulk is not affected by the electrolysis at the electrode surface. So all important phenomenon occurs at the diffusion layer. So this is a typical voltammogram. You can see here. Here are the concentration profiles. In the beginning, I'm going to talk about reduction. An oxidation. So you have a head species here. It's going to be oxidized, losing an electron. Here's the voltammogram. I'm going to change the potential from 0 volts to 0.8 volts. I'm going to oxidize this material. So now the idea is to interpret the shape of the voltammogram. I have 2 questions to you, and let's try to understand why in a cyclic voltammogram you have the duck shape. It looks like a duck. So the first question is why you have a peak, then why current decreases after the peak. 3, why you have first anodic current. You can see here, positive means anodic. Then in the reverse scan, you have a cathodic process. So let's try to understand that.
I'm here checking the chat and try to, if someone would like to say something, yes. I could open the mic.
Okay, let's start from the potential A. At the potential A, the species red is at the surface, but the potential is not positive enough for the oxidation to take place. So the species A coexists with the electrode surface. But when the potential is close to 0.2 volts, 0.3 volts, the reaction starts. So an oxidation process takes place. You can see here at B, the profile, the concentration profile is changing. You have less red at the electrode surface. Here is distance, here's the concentration, and you can say that at this potential region here, the material is close to the electrode surface, but the potential is still not very positive for the diffusion be the limiting process. So when you start to apply a more positive potential, then more material can be oxidized, current starts to increase until you reach this potential here. Now you have what you say a peak potential, peak current. In this case, current reaches its maximum value. Then it starts to decrease. Why does this happen? Is the first question here. Any idea?
We have something. Gabriel is saying something in the chat. The peak represents the electron transfer to the oxidation process. The current decrease due to the red species concentration decrease at the electrode interface.
Yeah, it's something more like this. So
and there is another one.
Yes.
There's a lot of thinking in the chat now. I think it's the kinetic transition. There is one. Joseph say
Yes.
After the peak diffusion, it's not enough to regenerate the species at the surface to keep the current increasing. That's why it decreases.
Okay, so let me try to help you. When potential is made more positive, the species can be oxidized. So you give more energy to the system, more material can be oxidized. So I'm going to show in the next slide that when the species red is removed from the electrode surface, you start to increase the thickness of the diffusion layer. So for the material to be oxidized, it has to reach the electrode surface. As the thickness of the diffusion layer is increasing, it's more difficult for the material to reach the electrode. Then from this potential here, what is going on is that the material cannot reach the electrode surface at the same rate, then current starts to decrease. I'm going to talk about this in a few minutes again. So at potential A, the concentration of red is maximum. Red coexists with the electrode surface. At this potential region, you have both species in solution at the electrode surface, red and ox. At potential close to the C region, the concentration of red is 0. All red is converted to ox. Then when revert the potential, now the potential is going to be less positive or more negative. If one has a reversible process, ox can now be reduced to red. You have a cathodic process here. You can see that the peak potential in the reverse scan is almost close to the anodic peak. I'm going to talk about this in a few minutes. So, if you see here...
Sorry, Mauro, there is a question here.
Yes, please.
Rona is talking about, does the CV shape change when if you had, she's mentioned about the out sphere and inner sphere mechanisms, if the CV changes.
Okay, I'm going to talk about this later,
Perfect. No problem.
When I'm going to discuss reversible and irreversible process.
Okay.
So this is the diffusion layer. You can see here that the profile changes at increasing times. In the beginning, all material, in this case red, is at the electrode surface. When the potential is made more positive, then the reaction starts, and the electrode surface has less material as a function of time. It's important to remember the slope of these curves here represent current. Current is flux, the flux of material that is converted, in this case, from red to ox. The amount of material that in this case is going to be oxidized. In the beginning, you have plenty of material close to the surface. When the time increases, you have less material, so current starts to decrease. We can also change the scan rate in a cyclic voltammetric experiment. As one can see here, there is a change. Question again is, when we increase the scan rate, the peak current increases, both the irreversible system, the cathodic and the anodic. How can I explain that? Tiago?
I will try to. We have two other different questions here until they try to reply to you. Primaggio is saying, what is it means of inverting the scan rate signal? It means why the species start producing even at positive potentials.
Sorry, Tiago, I did not understand that.
Oh, the first question, Primaggio say, what is it means of inverting the scan rate signal? He would like to say what happens if you change the signal of the scan rate, positive or negative.
The scan rate is not negative. Well,
I think
in this case here, in this slide, I'm going to change the scan rate. It's going to be, in this blue is a slow scan rate, in red, a very high scan rate. When I increase the scan rate, you can see a change in the voltammogram. You get more current if the scan rate is higher. The question is, why is that? Why you get more current if the scan rate increases? For instance, this can be 10 millivolts per second, 50 millivolts per second, 100 millivolts per second. That's the question. Why we get more current if the scan rate increases?
We have an answer here. Peak increase with the scan rate because the diffusion layer is thinnest.
Perfect. Yes, perfect. It always has to do with the time window. If the time window is short, by short, I mean high scan rate. If the scan rate is very high, the time window is short. If the time window is short, the thickness of the diffusion layer is very small. If the thickness of the diffusion layer is small, the material is close to the electrode surface, so you get more current. So remember that. This is very important. If the diffusion layer is very
Hold on a little bit, Mauro. We have another question here.
Yes.
Abdul is saying, at the peak, is the concentration of red and oxidized species are the same?
Oh, here. Yes. Look, here at this potential range, you have at the electrode surface only red, no ox, because the reaction is not happening. From here, now you have red and you have a very small amount of ox. At B, at the potential, now at potential B, you have the same amount of red and ox. And at potentials more positive, there is no red and you have only ox at the electrode surface. Okay?
We have another, it's an answer for your last question. Lower scan rate allow the species to diffuse more to the electrode. Showing the different point, talking about not the higher scan, but talking now about the lowest scan.
Yes.
The species could diffuse more.
Yes. Remember always, if the scan rate is small, the diffusion layer, the thickness of the diffusion layer increases. The material has to come from a very far position to the electrode surface. That takes time. So because of that, current starts to decrease. If the scan rate is very high, the time window is short, the diffusion layer is very short, the material is close to the electrode surface, current is much higher. Okay? So when you have a voltammogram, this is a typical voltammogram, is the oxidation of ferrocyanide to ferricyanide. How can you measure the anodic peak and the cathodic peak? The anodic peak is very easy, but you have to take care. The other peak is not from 0 to here. It's from the baseline. You have to extrapolate here. And this is how can you measure the cathodic peak current. For a reversible process like ferrocyanide, ferricyanide, you should expect both values for anodic current and cathodic peak currents. In cyclic voltammetry, another very important issue is the distinction from capacitive current and Faraday current. The capacitive current is proportional to the capacitance of the double layer and the scan rate. The Faraday current depends on the concentration of your electroactive species. The potential stat measures the total current, which is a sum of capacitive current and the Faraday current. So my question now is as follows. The capacitive current has a significant contribution to total current if the scan rate is very high. So if your CV is recorded a very high scan rate, you are going to have a very high capacitive current because capacitive current depends on the scan rate. Here is an example. For a typical capacitance of the double layer, this is the value. Look, the capacitive current can change from 2 microamperes at 100 millivolts per second to 2 milliamperes for 100 volts per second. So the capacitive current depends a lot on the scan rate. And of course, if the concentration of the electroactive species is low, then the fraction of the current that depends on capacitive current increases. That's very bad for analytical point of view. Look at this plot here. It's showing the total current as a function of the concentration of the electroactive species. As we can see here, the capacitive current does not depend on the concentration of the electroactive species. But the Faraday current, yes, depends on the concentration. It's a linear dependence. So my question is now, you have here a voltammogram. In red is the voltammogram of ferricyanide. In blue is the voltammogram of the supporting electrolyte. Can you distinguish the voltammogram in red from the voltammogram in blue? So, is the Faraday current distinguishable from the background, from that of the background? In this case, in this particular case, what can you say? Can I, from analytical point of view, my idea is to distinguish the Faraday current from the background. That is what all analysts, chemists want to do, to get a signal that's different from the background. In this case, I think, yes, I can do that. Thiago, can I try to use my...
Yes, yes. There is an answer here in the chat. Yes, it's possible.
I'm going to move from here.
Okay.
Can you see it?
Not yet.
No?
Try to share the full screen again, Mauro. The whole screen.
Sorry. Share screen?
Yeah.
It's here. Can you see it?
Yes.
Okay. My pen is not working, so I'm going to use my mouse. I'm going to draw the voltammogram for supporting electrolyte, KCl. It's not good. It's not going to be nice, but I'm going to try. I think it's okay. So this is, sorry, a voltammogram for the supporting electrolyte. Now I am going to show you the voltammogram of ferricyanide at 1 millimolar concentration in supporting electrolyte. It's going to be something look like that. Sorry, I'm not a good drawer. This is the voltammogram of ferricyanide, 1 millimolar, okay? So this is 1 millimolar. Now I'll try to do that for a solution 0.1 millimolar, 10 to minus 4 molar. How is going to be that voltammogram? If the concentration decreases tenfold, the current decreases tenfold. Let me try. So this is 10 to minus 4. What happens if I try to do that for 10 to minus 5? For 10 to minus 5, I'm not going to distinguish the Faraday current from the background. So, Thiago, I'm going to come back.
Perfect.
Can you see it? Not yet?
Not yet. Try to close this one and share again. Yeah. It was a good image for a mouse draw.
Yes, yes. I trained before. Can you see it? No?
Oh, no. Try to share it again, the full screen. You are trying to share the PowerPoint now.
What's going on? Oh. Is it?
And you need to put in the no, it's not working now. Try to share again the full screen mode. I think that you share a window.
Okay. Yes.
Okay, try to put in the full mode.
Yes. Not yet.
It's not in the full mode for us.
And now?
Perfect.
Okay. So again, cyclic voltammetry is not good as an analytical tool. To do that, you can change the technique. There are some techniques that are called pulse techniques. They are better for get analytical information from a system, but not using cyclic. So this is a typical electrochemical cell. You have the working electrode, the auxiliary electrode, the reference electrode. In a 3-electrode system, current flows from the working electrode and the auxiliary electrodes, and current is not driven through the reference electrode. So you can control the potential of the working electrodes using the reference electrode, but current flows from the working electrode and the auxiliary electrode. So the potential does not change. The reference electrode potential does not change because current does not flow through the reference electrode. You can see here that there is a possibility to bubble an inert gas. Do you know why? You can sometimes, not always, but sometimes bubble an inert gas. By inert gas, I mean nitrogen, argon. Why should you do that? At some conditions. Thiago, I think someone knows that. Why sometimes I have to bubble an inert gas?
To eliminate the oxygen at the solution, primário say at the chat.
Why?
Inert gas is to eliminate competition of reaction, Arsha say, purge and to remove oxygen, and
Yes.
Nazim say the same, and primário
Yes.
say to eliminate the oxygen at the solution.
Yes.
And we
Especially
have another one here only to check. Oh, because the oxygen is electroactive.
Yes. If we work at negative potential, dissolved oxygen is going to be reduced as well. So you cannot want to measure the oxygen signal. You have to eliminate oxygen. You can do that by bubbling an inert gas, something like argon or nitrogen for 5 minutes, 10 minutes, depending on the flow. As the reference electrodes, this is the typical hydrogen electrode, but it's not easy to work with a hydrogen electrode because you have to bubble hydrogen. It's not easy to do that. Then use 2 different electrodes, reference electrodes. Calomel electrode, these are the reactions. The potential against the hydrogen electrode is 0.224. This is I think the more used reference electrode is silver chloride. The potential is almost 0.2 volts against hydrogen. Here you can see how we can convert the potential by using the silver electrode and the mercury electrode against the standard hydrogen electrode. Talking about working electrodes, you have plenty of materials. Remember that the electron transfer rate depends on the material. This is very important. You can use solid materials, platinum, gold, carbon, here, silver, liquid metals, mercury, carbon, graphite, diamond, glass carbon. There are plenty of carbon materials and sometimes semiconductors. The electrode geometry can also change. From disc, you can use a disc electrode in stationary solutions, or let's see if you can talk about this. In a rotating disc configuration, you can have hemisphere, cylinder, and micro or nano electrodes. If I have time, I'm going to talk about micro electrodes. The morphology can also change. You can use bare surfaces, sometimes nanoporous surfaces, or modified surfaces. Modified surfaces are those that can have some films, carbon nanotubes, graphenes. The idea here is to facilitate the electron transfer process by anchoring some mediators on the electrode surface. For the solvent, it's very important because the potential window of the experiment can change depending on the solvent. Of course, you have to look at your electrolyte. It can be solvent, organic solvent. In aqueous media, you can use platinum. Look, mercury, you have a problem. For positive potentials, we cannot use mercury at positive potentials because mercury is going to be oxidized. Mercury is good in acidic solutions and at negative potentials. Platinum and carbon both work well from 1 volt positive to -1 volt. Sometimes for platinum, you can use organic solvents. Here, as one can see, there are some ionic liquids or organic salts. So now let's see what kind of information you can get from cyclic voltammetry. If you have a reversible system, as I showed you before, the peak current is given by this equation, the Handler-Stevich equation. Here's the equation. N is the number of electrons, A is the electrode area, C is the concentration, D is diffusion coefficient, and this is the potential scan rate. Again, if the potential scan rate increases, the peak current increases. For a reversible process, there are some diagnostics. The first one is that the peak current depends on the square root of the scan rate. So if you have some voltammograms at different scan rates, if you plot peak current as a function of scan rate, you can get a straight line if you have a reversible system, if the current depends on diffusion. Another diagnostic is the ratio between both anodic current and cathodic current is almost 1. You can get information on the standard potential, is the average between both peak anodic and peak cathodic potentials, and both peak potentials do not depend on the scan rate. So these are some diagnostics for a reversible system. Here are two very important messages. First one, if you have a reversible system, both species, the oxidized and the reduced, they are always at equilibrium with the electrode at any potential. That's because the electron transfer step is very fast. This is very important. If the electron transfer step is very fast, diffusion is the rate limiting rate, and you have a, what we could say, as reversible system. Another important message from a reversible cyclic voltammogram, you can get information on the thermodynamic potential, but you cannot get information on the kinetics of the electrochemical process. Now, for an irreversible system, they are characterized by a sluggish, slow electron transfer. In this case, the peaks, both the oxidation and the reduction, are separated. And here are the equations that can characterize this process. You can, for an irreversible system, yes, you can get information on the standard heterogeneous rate constant. Potential depends on the heterogeneous rate constant. And you have reversible system, we have irreversible system, and you have something in the middle. They are called quasi-reversible system. The rate change from 10 to -1, the electron transfer rate changes from 10 to minus 1, 10 to minus 5. 10 to minus 5 are for irreversible system, 10 to minus 1 are for reversible system. So for quasi-reversible system, current depends on both the charge transfer and diffusion, mass transport. The voltammograms change, as one can see here. The shape of the voltammograms change. And the information that you can get is here. You can get the rate constant by change the scan rate. I'm going to show this here.
Sorry, Mauro, to interrupt you. We have a question here in the chat.
Yes, please.
Primage say, Professor, if we can find the double layer capacitive current, can we subtract it from the total current to find the peak current? This is a question about if it's possible to subtract the, yeah.
Ah, yes, but yes. Yes. Primaggio?
Yeah.
Primaggio, yes, but this is an old slide. If you can subtract the background current, then you can get the analytical information. Some potentiostat can do that. Then can remove the Faraday, the capacitive current by subtraction. In this particular case, yes, you can get the information, the analytical information, by removing the capacitive current by a kind of subtraction. You can do that. There is a technique, I can talk about it later. It's called fast scan voltammetry. In fast scan voltammetry, the voltammogram is recorded at very fast scan rates. So in this particular case, the background current is very high. But if you subtract the background current, it's possible to do that. Depending on the potentiostat, in this particular case, you can, after subtraction, get the information on the Faraday current that's proportional to the concentration. Yes, Primaggio, you can do that.
Primaggio say, okay, thank you in the chat.
Okay. Let's move now to the transition. This is, I think, is one of the most important slides. When you say that a system is reversible or it is irreversible, you have to take care, because this always depends on the time window. So you can have a transition from reversible to irreversible depending on the time window of the experiment, which means that the mass transport, you have a very big influence. For instance, an electrochemical process can be seen as reversible or irreversible depending on the experimental conditions. I mean the time window. Let me show you now.
Until you show that we have a question here.
Yes, please.
GL is saying, why is it more indicated to obtain parameters like current peak and peak potential from the first voltammogram or the other ones? If you try to record a large number of voltammograms, like successive voltammograms, what is better to get the value?
That's a very difficult question to answer. And sometimes the material is adsorbed on the electrode surface. If that happens, the second voltammogram has no relationship with the first one. So in this case, you cannot get the information the student asked, because the surface of the electrode in the first voltammogram is different from the surface in the second voltammogram, because something accumulated on the electrode surface. So if there is no adsorption after the first voltammogram, I would expect that all voltammograms, the first one, the second, the third, all of them were similar. So there is no difference between the first one and the second one. But if after the first voltammogram, something adsorbed on the electrode surface, then you have a problem. then your question is difficult to answer. I hope I can help you. It's not easy, especially if there is some kind of adsorption of the electrode surface. So, can you move on, Thiago?
Yes, Jerry say thank you in the chat for your answer.
You can talk about this later. So, the rate of the electrokinetics is measured by the electron chemical rate constant. So the electron transfer rate depends on that parameter. And the rate of mass transport depends on the mass transport coefficient, which is given by the diffusion coefficient and the thickness of the diffusion layer, which depends on time. So as we can see here, the distinction between fast and slow electrode kinetics always depends on the rate of mass transport. I mean that if your electron transfer rate is higher than the mass transport rate, you can say the process is reversible. So in this first case, diffusion plays a key role. On the other hand, if the rate of electron transfer is low compared to mass transport rate, your system can be said to be irreversible. So the idea is always to change the mass transport rate. If you want to get a kinetic information, if you want to probe the kinetics, you have to change the mass transport rate. The idea is to establish a kind of competition between electron transfer rate and mass transport. Remember, mass transport depends on the time window of the experiment. That's why mass transport is so important. The idea is to change the mass transport. So, as I have some time, I have a few minutes.
We have one question here, Mauro.
Yes, please.
Oh, it's about the. These questions are not so easy sometimes. Does it mean high Denuault number always represent reversible process?
What? I didn't understand the.
I didn't understand the Denuault number. Abdul, would like to do your question using the mic?
Yes, please.
If you would like, I can open your mic. Raise your hands only to say something. I will.
I'll be pleased to hear you.
I will check. Where is he? I open his mic. If you would like
Hello.
to. Perfect. Oh, great. Thank you.
You can hear me?
Yes, perfect.
Professor, my question is, if I have really fast reaction compared to the rate of diffusion, that means I will have really high Denuault numbers. So does high Denuault numbers always represent reversible process, and low Denuault numbers, they represent non-irreversible process, something like that?
Abdul, I didn't understand column number. What's that?
Maybe I spelled the name of the number. It is, I'm just.
Can you understand that, Thiago? The
No,
number.
It's the same. The people in the chat is saying, what is this number?
Yes, I don't understand that.
It's actually written in this form, like.
I think that the Denuault number is the K0. It's about the kinetics of the reaction.
The electron transfer rate.
Yeah.
The electron transfer rate is the rate of the electron, the transfer at the electrode surface. So the idea is always to compare the electron transfer rate with the mass transport. Both can control the current. Abdul,
Yeah, I'm listening, Professor.
yeah, can you explain your doubt? I didn't understand very well.
So I'm writing an expression how the Damköhler number is. So Damköhler number is actually expressed as the reaction and K times the diffusion length divided by diffusivity of the species.
I didn't understand.
The Dunn-Kohler number is it's about the transport. It's like a transport phenomena that occur in the system. If the transport's higher or lower, it's like the diffusion.
Yes. So this number is something related to the mass transport.
Yes.
So the idea, Abdul, is to compare mass transport with the kinetics of the electron transfer rate. So it's here. If the mass transport is not so high, so the electron transfer rate is not the rate limiting. So the process is called reversible.
Okay, now I understand, Professor. Thank you.
Okay. You can talk later.
No problem.
Let's just move to an example. Maybe it's going to be clear. Let's understand the influence of scan rate on the shape of the voltammogram for a coupled chemical reaction. You have a species, I call it A. It's going to be, in this case, oxidized to B, but B can be converted to C. This is the heterogeneous rate constant. This is the homogeneous rate constant. Suppose the homogeneous rate constant is 10 seconds, 10 seconds minus 1. Here are the voltammograms, the CVs. They are normalized because remember, the scan rate has a very big influence on the peak current. But if you normalize, all of them are similar. My question is, here are the CVs recorded at different scan rates for this system here. They change, the scan rate changes, I think, from 1 millivolt per second to 500 millivolts per second. Who can show me, who can tell me which is which? When I get the black voltammogram, when I get this yellow voltammogram here, at a very high scan rate or a very short, a very slow scan rate? Now I'm asking you. There are voltammograms here. They will record at very fast scan rate, I think 500 millivolts per second, and very slow scan rate, 1 millivolts per second. You can see here how the voltammograms change a lot. In this case, I cannot see the reverse peak. But in this case, the voltammogram looks like reversible. So yes. The question is,
Paul Newman say that the higher scan rate means it's the black one, and yes. Brona say that the low scan rate is the irreversible one.
Yes, perfect. So here are the legends. So at 500 millivolts per second, the time window is very short. There is no time for B to be converted to C. In this case, the voltammogram looks like a reversible voltammogram. On the other hand, at 1 millivolts per second, I lose B because B is converted to C. In the reverse scan, the electrode does not see B. That's why the shape is similar to an irreversible voltammogram. So as one can see here, the time window is very important to see a system as a reversible, as in black, or irreversible as yellow. You can also change. You can see the influence of the rate constant, in this case, Kf, at a fixed scan rate. This is a typical system. The species can be oxidized in an electrochemical step, here, A to B, and B can be converted to another species. I call it a C. As one can see here, if the rate homogeneous rate constant is high, is blue, B can be converted to C. In the reverse scan, I cannot see, the electrode cannot see B. You can see an irreversible voltammogram. On the other hand, if the rate constant, homogeneous rate constant, is very low, the reaction does not take place at the time window of the experiment. So in this particular case, the voltammogram looks like the one of a reversible system. Let me move now, if I have a few minutes more, to voltammograms record very small electrodes. We call them as a micro electrodes. So if I have I call it as macro big electrode, the diffusion is always something like that. We call it a planar diffusion. But if you have a micro electrode, for a micro electrode, its size is the micrometer range. If the size in the micrometer range, after a few seconds, when I say not few seconds, sorry, a few milliseconds, the diffusion changes from planar to radial, convergent diffusion. So the material goes to the electrode surface very efficiently. In this case, as one can see here, the voltammogram is completely different. You cannot see the duck shape, but you can see a sigmoidal shape. This is a voltammogram of ferrocene being oxidized to ferrocenium. I have two questions. Why there is a steady state situation? Why you cannot see a decrease in the current after you reach the peak for a micro electrode? Remember, for a micro electrode, the diffusion is very, very efficient. It's different from a macro electrode. For a macro electrode, you have planar diffusion after a few milliseconds or seconds, depending on the time, on the size. The material, you create a diffusion layer that's different for a micro electrode because the diffusion is very efficient. So why is someone able to help me here? Why there is no peak current but a sigmoidal voltammogram?
We have an answer here in the chat. Because there's more than one answer. Because of the thin, because the double layer is thin, a steady stain is obtained, and there is no mass transport. There is mass transport.
Yeah, I think there is mass transport. Yes, it's always you have mass transport. But for a micro electrode, because the size of the electrode is very small, the diffusion from the solution to the electrode is very efficient. So the material reaches the electrode very efficiently. So at same rate, that's very important. So
Abdul say something important here, Mauro. I think that we'll link that we will talk. The electrode and the fusion layer are comparable in size.
Yes, 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 perfect. That's correct. Who said that?
Abdul say that.
Yes, thank you very much, Abdul. That's perfect. Yes, you are correct. So that's why you have always a sigmoidal voltammogram. The material reaches the electrode very efficiently. The size of the diffusion layer is close to the size of the electrode, as Abdul said. In the reverse scan, you cannot see a peak. Why? Because the material reaches the electrode very efficiently. And of course, it leaves the electrode, the generated product, in this case ferrocinium, also very efficiently. So the transport to the solution, from the solution to the electrode, and to the electrode, from the electrode to the solution is very fast. So the electrode never sees the ferrocinium close to the electrode surface. That's why you cannot see the reverse process in a voltammogram recorded with a microelectrode. I'm talking about microelectrode because especially the second question, I'm going to advance. If you change the radius of the microelectrodes, you can change the mass transport rate. This is very important. If you change the radius of the microelectrode, the mass transport rate increases. Then you can probe the kinetics of an electrode reaction. You can also do that, if I have a few more minutes, Thiago, by using convection. As one can see here, you can record a voltammogram with, here you have a 2 millimeter electrode. It's a big electrode. As one can see here, is in ferrocene medium. You can see here the typical voltammogram, the duck voltammogram, in silent conditions. Silent means stationary conditions. Insonation means convection. If you have convection, you can see a change from here to here. Thiago, I'm going to ask them again. What kind of difference do they can see from A to B? There are a few differences from A, stationary solution, to B, convection, convection by insonation. Remember, now I have a big electrode, a macro electrode. What are the main difference from A to B? Remember, I have a macro electrode, stationary conditions, the duck shape, but B, I have insonation. Insonation being convex, means convection.
Until answers, Mauro, we have a question here from Andrea Fassano. And in the case of microelectrode, the redox potential of the redox couple would be in the middle point of the sigmoidal shape.
Yes, perfect. Yes. What about these two voltammograms?
In B, mass transfer is due to the convection.
Yes, perfect. Yes. So in B, you have
additionally,
convection.
Mauro, only to help you with the Dunkholer number. The Dunkholer number is a number using the chemical engineer. It's to talk about the transport and chemical reaction.
Okay.
And
okay.
It's possible if you have diffusion, there is a number. If you have convection, you could increase the number of that.
Okay.
It's about what we are talking now. Yeah.
Okay. Yes, it's similar to that. So in B, you have diffusion and convection by insonation. So you can push the material to the electrode surface more efficiently by using insonation. So the changes here are, first, you get more current. You can see the scale here, much more current, because the material is going to the electrode by also convection, insolation. And the shape changes from planar to convection. Now the material is going to the electrode, and you cannot see the reverse peak because the material goes to the electrode very fast, and the product is removed from the electrode very efficient. So
Mauro,
you can also do that.
Mauro, sorry, we have a
Yes.
good question here in the chat.
Please.
Paul Newman is saying that I don't understand why if we decrease the radius of the electrode, we improve the performance. Because he complements that. Because if we have a higher radius of the electrode, we improve also the possibility of the area for the diffusion layer.
Yes, yes, that's true. Yes. Who said that? Paul.
Paul Newman.
Paul, can I try to explain this later? Today or tomorrow during Gabriel's talk? Can you do that tomorrow?
Gabriel, tomorrow.
This is very important. I'm not going to forget you, Paul.
Perfect.
Yes.
Okay. He say yes, for sure.
Okay. Thank you, Paul. So let's just move to another way to increase the mass transport rate. You can rotate the electrodes. When you rotate the electrodes, you can see that the limiting current depends on the rotation rate. And there are some equations. This is the Levitt equation that shows that the limiting current depends on the square root of the rotation rate. And you can also use a disc electrode in a disc ring configuration. This is much more important because you can generate a product at the disc and it's going to reach the ring. So you can get information on a material that is generated at the disc. So the idea is to, for instance, if I have an oxidized species, it is going to be reduced. O receives electrons, goes to red, and red is oxidized at a certain potential at the ring. And if the product that is generated at the disc is stable in solution, you have what you call as collection factor or efficient. It's the ratio between this current at the ring and current at the disc. Remember, the electrode is going to be rotated in solution, as it's shown here. This is called the collection efficiency or collection factor. It's current at the ring, current at the disc. Let me ask you two questions. Why the current at the ring is smaller than the current at the disc? Who can try to explain? Remember, the electrode is rotating on the solution. There is a disc, there is a ring. Why current at the ring is smaller than current at the disc? It's always. So the collection factor is always less than 1. There are two reasons. Who can explain that?
We have answers. Yes, we have answers here, and we have a question. I will start with the answers. The answers are here. The first one is because of the diffusion of the species. The second one, due to the difference in velocity in the rate of the species arrived at the electrode, because the current of the ring depends on the species formed at the disc.
Yeah, something like that. So the first question, the first answer, you can see the area of the ring is not the same as the area of the disk. The area of the ring is always less than the area of the disk. That's the first reason. But the other reason, it's more important, is because the material that is generated at the disk, it goes to the solution, it disperses the solution, and a fraction of this material reaches the electrode surface. So a fraction is reached the electrode surface and is measured, it's seen by the ring. So that's why current at the ring is smaller than current at the disk. But for a reversible system, for a stable material, the collection factor does not depend on the rotation rate. Remember that. So the second question, what's the relationship between the flight time? Flight time means the time from the material leave the disk and arrive at the ring. Remember, it's important because I can get kinetic information. If I have a small rotation rate, and if I have a very fast rotation rate, what's the relationship between rotation rate and the, I call it just flight time, the transit time from disk to ring.
Abdul say that it's inversely proportional.
Yes, yes. If the rotation rate increases, the flight time or transit time is smaller. So these are rotating ring disk voltammograms for ferricyanide, the couple ferricyanide, ferrocyanide. You can see current at the disk, current at the ring at different rotation rates. The important thing here is that if I measure current at the ring and current at the disk at different rotation rates, the value is always close to 0.4.
Sorry,
For this,
Sorry.
yes.
There is two questions here. One is an old one, but I think it's important to try to answer. It's about, where is the question? It's here. The question is about how does the change in concentration affect the diffusion? I think that it's important to understand the process. The question is about how the concentration changes the diffusion.
How the concentration changes the diffusion?
Yes, I think that the answer is the diffusion is not changed. The diffusion is always the same. The driving force could be different. Yeah.
Yes, perfect, perfect, perfect.
And so, the other one, sorry, Mauro.
Yes.
Paul Newman said that he didn't see how it's. I think that's about the inversely proportional. How the flight time it's inversely proportional to the current.
No. The question is what's the relationship between the transit time, the time for the material,
sorry,
leave the disk and arrives to the ring. If the electrode rotates at a higher rotation rate, there is less time for the material goes from the disk to the ring. I think is that clear?
I think so. There is a question related to this slide about the collection number then, and because the question is why the collection number is to 0.4. Can you explain, please? This is more related with the geometry, but I think that
the collection efficiency is this, the current at the ring, you can see here, and the current, the ratio between current at the ring, current at the disk at the same rotation rate. If you measure current at the ring, current at the disk for the different rotation rates, the value you can see here is close to 0.37, almost. Okay? So, Thiago, it's close to 10:30. Can I continue tomorrow? Because tomorrow Gabriel is going to talk about reaction mechanisms. And these are classical reaction mechanisms. I think it's better. Then I can continue with, I can arrange with Gabriel to show this slide and a few others tomorrow. Can you do that?
No problem. No
I can
problem.
arrange with Gabriel.
No
Then
problem.
I can pass my time. It's almost 10:30.
Okay, I think that it's good only to answer again the about the collection number, because I think that the question is still here in the chat. I understand the meaning of the collection number, but always is 0.4. This is not true. The value is 0.4 because of this type of geometry and this type of reaction. You can change the collection number.
Yeah, but for a reversible system like ferrocyanide, the generated product is ferrocyanide. It's stable. If the species is stable in solution, the collection efficiency is not going to change independent of this rotation rate. I'm going to talk about this because I think today I cannot do that. Look, if you have a system, this copper 3 triglycine, we will see that the collection number changes depending on the rotation rate. And you can extract kinetics information from this system by changing the rotation rate and measure the collection efficiency. But I think it's now too late, Thiago. I'm going to talk about this tomorrow. Okay? I can arrange with Gabriel.
No problem. Okay, only one last question.
Please.
There is a curiosity from Andrea Fazano. Curiosity is if we have time regarding microelectrodes, are there normal size electrodes composed by multiple microelectrodes to optimize mass transport, but also max current?
Yes. I'm going to talk with Gabriel. In Gabriel's talk, we can explain that tomorrow, okay? Perfect. I can arrange with Gabriel, and you can talk about the reaction mechanism and include some more information, microelectrodes, and these two final examples, okay? I can do that tomorrow.
No problem.
Thiago, just to finish, I would like to show this paper. This paper is very important. It's a paper published in the Journal of Chemical Education 3 years ago. Is a practical beginner's guide to cyclic voltammetry. So for those who are interested in cyclic voltammetry, please take a look in this paper here. It's very nice. It's very simple. It's for undergrads, but it cannot be extended for graduate students. Okay?
Okay, thank you, Mauro, for today.
Thank you very much for tomorrow.
We'll have more. No problem.
Okay.
There is a lot of people.
If you allow me, I can come here tomorrow again.
Okay, no problem.
Otherwise, I can transfer these final slides to Gabriel.
No problem. We
I'm
can
going to talk to him.
It will be a pleasure to have you here. A lot of people say in the chat, thank you for the amazing class and for the provocative part. Yeah, thank you very much, Mauro, for that. And
my email is here, Thiago. This is my email. Show to them. I can talk to you today, maybe tomorrow, or anytime.
Yeah, try to arrange with Gabriel about.
Okay.
And you are permitted to come here. Thank you very much, Mauro, again. And we will have a break now from 15 minutes break until the GIS lecture. Thank you very much again, Mauro. If you could stop to share your screen because I need to put the timer again.
Bye-bye, Thiago.
Bye-bye, Mauro. See you tomorrow.
See you tomorrow. Bye-bye.
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 everyone. Welcome again. And now we have our next speaker, Guy, will return now to talk with us about modeling. I'm a huge fan of the lectures from Guy. Thank you, Guy, again to come here today, and we will have a pleasure to listen to you tomorrow again. And now the stage of the Zoom room is yours. Thank you very much again for all the help with this school, with this project. Thank you, Guy.
Thank you very much, Thiago. Can you confirm that you can hear me and you can see my slides?
Everything perfect here.
Okay, good. Well, good day, everyone. So this is the second part of this lecture on modeling. And we're going to start with a quick revision of what we did yesterday, just a couple of slides. And then I want to move on to other examples of what we can do with this very simple explicit finite difference algorithm that we saw yesterday. And essentially, I want to show you how we can implement more and more complex electrochemical problems. So we're going to look at incorporating different potentials, because what we saw yesterday was just a simple potential step for one potential value, but we always explore different potential windows. So we're going to see how we can do that with in chronoamperometry. And from this simple problem, we're going to move to a technique which is called sampled current voltammetry, which illustrates the relationship between current, time, and potential. And I will briefly show you an example of how we can implement double potential steps in the simulation, and that will lead to cyclic voltammetry. And I will show you how we implement cyclic voltammetry, and then we'll move on to cyclic voltammetry with two species, because until now we have made the assumption that it was sufficient to work with one species, but I want to show you how we can do that with more than one species. And then we're going to incorporate electron transfer kinetics, and this will lead on very nicely with what Mauro has just been presenting. And then we'll follow that with coupled chemical reactions, and I will show you how we can implement the kinetic scheme, the reaction mechanism in the solution. And I will show you how we can simulate the ISE mechanism, the one you've just seen with Mauro. And we're going to finish with a completely different model, where instead of having potential static control of the electrode, we're going to look at a very simple simulation where we're going to look at galvanostatic control. So we're going to switch to imposing the current as opposed to imposing the potential on the electrode surface. And you're going to see how we can very quickly modify the model that we have built and incorporate galvanostatic control. So just to recap what we saw yesterday, we came up with this explicit finite difference, EFD, numerical scheme, which allowed us to compute a concentration in space and time. And the best way to look at it was to use this matrix. So we had the vertical axis representing time in the form of iterations within the simulation, and the horizontal axis was representing distance in the form of the index, which represents, if you want, the mesh that we're using to discretize space. So you can think of this as a mesh in time and a mesh in space. And this concept of mesh is quite useful, because tomorrow when we will look at the finite element method, you will see that the concept of the mesh is very important because it really defines how well we can control our simulation. So with the explicit finite difference scheme, we had this very simple relationship which allowed us to calculate a new concentration knowing the previous concentration. So here I represent it as K being the present and K plus 1 being the future. And so with this very simple relationship, I could calculate the future knowing the present. I will show you some examples today where instead of using k+1 and k, I will use k and k-1, which means calculating the present from the past. It's exactly the same thing. And so just I will highlight it as we go along. And remember the lambda value, this was what I call the dimensionless diffusion coefficient, which was essentially a relationship between the space increment delta t and the time increment delta t and the space increment delta x. So we had delta t over delta x squared. And I showed you that lambda couldn't be bigger than 0.5, couldn't be equal or bigger to 0.5, otherwise the scheme was not stable. And I showed you that by zipping through from the bottom of the matrix to the top of the matrix, we could compute all the values in the box in blue, and that allowed us to compute all the concentration profiles throughout the evolution of the experiment. And this was made possible because we know the bulk, the condition that we impose in the bulk. So this is the boundary condition in the bulk. We know the initial condition, which is what was in the cell, if you want, the concentrations we have in the cell at the beginning. And we either know values or we know relationships between surface concentration and gradients, for example, on the electrode surface. And this was the boundary condition on the electrode. So essentially, everything remains the same. But when I go from one problem to another, one model to another, what I do is simply change the conditions on the electrode surface. So all we're going to see today is how we implement new conditions on the electrode surface to allow us to simulate new problems for our electrochemical experiments. So the outcome yesterday, when we did the potential step, we simulated the evolution of the concentration profiles. We measured the gradient of the concentration profile next to the electrode, and this is the current, essentially. So we could see that within a very small number of iterations, about 10 iterations, we already had really smooth concentration profiles. And this was just to show you that the scheme, although it's not very efficient, it actually works quite well. So today we're going to start with an improvement on the simulation we did yesterday. And essentially what I want to do is to simulate the chronoamperograms by stepping from a value EI, where there's no reaction running, to any value along the potential window up to EF. So essentially, I want to see what the electrode current is going to be as a function of time for potential steps anywhere along this potential window. This is what you would get if you did a voltammogram, if you recorded a voltammogram with a rotating disk electrode or with a micro disk electrode in the steady state. So I'm expecting to see the current dropping as a function of 1 over the square root of time, as we saw yesterday. But what I want to know is how is this going to be affected by the value of the potential, the target potential. So going back to what we saw before, we had transport equations for the reactant and the product. We had the initial conditions, which basically described what we had in the cell initially. And well, that remains the same. Nothing is changing here. We have a new boundary condition. And this is a relationship between the electrode potential and the surface concentration. So maybe I forgot to mention just before, I'm assuming planar diffusion as we did yesterday, but the new assumption is fast electron transfer kinetics. So I don't want to have any electron transfer kinetic complications in this simulation. So this is the reason why I am using the Nernst equation to relate the electrode potential to the surface concentration. But what we need to remember is that the electrode potential or the step-in potential is the perturbation waveform. So I will need to somehow rearrange this expression to allow me to fix the surface concentration of the species on the electrode surface. So this is what I will show you today. The rest is the same as yesterday. No change here. We have equal and opposite fluxes of reactant and product at the electrode surface. So we can see that the gradients are equal and opposite. We take into account the diffusion coefficients. And then the third expression here on the boundary on the electrode is not a constraint, is simply the way to calculate the current from the gradient, the flux of the reactant. Far away in the bulk, we retrieve the initial condition. You can see that it's exactly the same as what we had in the cell at the beginning. So again, these three expressions haven't changed. So the only new thing is this Nernst equation on the electrode surface. So we need to see how we can implement that. Well, at this moment, I want to start from a simple basis. So I'm going to make the assumption that I used yesterday, which is that the reactant and the product share the same diffusion coefficient. Tiago, you've got a question?
Yeah, sorry. We have a question here in the chat from Rona. She is requesting about why we can assume equilibrium at the electrode surface, Nernst equation. The reason to, yeah.
Why? Well, imagine that I do this experiment with a very, very fast redox couple. For example, ruthenium-hexamine. This is an outer sphere electron transfer process, which is extremely fast. And on the most conditions, we can consider it as being so fast that the electrode current is always diffusion controlled. Later on, I will show you how we implement the situation where we don't have equilibrium, where we have combination of mass transfer and electron transfer kinetics. But for the moment, I want to start with a simple example, and that's why I've assumed that the two species were in equilibrium at the electrode surface. We don't have to, but for the point of view of teaching the concept, it's a good point where to start. But there are cases, as I mentioned with ruthenium-hexamine, there are cases where we can make that assumption.
There is a complementary note here. Rona is mentioned about, but the diffusion also gets you out of the equilibrium, but depends. I think that you will explain that.
No, the diffusion doesn't get me out of the equilibrium. No. If you have to think about the electrode process as being a sequence of two steps. The first step is you need to bring the reactant to the electrode. The second step, the reactant reacts, undergoes electron transfer, and forms the product. Because here I've made the assumption that the electron transfer process was extremely fast, the limiting step will be the mass transport, the diffusion. So I'm assuming, and this is why I said yesterday, you always need to start from very simple problems, so simple assumptions. Here I'm assuming that the electron transfer is so fast that the electrode is always waiting for the reactant to reach the surface to react. Later on, I will show you how to implement electron transfer kinetics to account for the fact that mass transport can be sometimes very, very fast. So if you were to do cyclic voltammetry with a microdisc electrode, I think yesterday I mentioned that people are sweeping up to 1 million volts per second, then the diffusion layer thickness is so small that the electrode is always fed with the reactant and never has to wait for the mass transport for mass transport to deliver the reactant. So there are cases where we have to account for electron transfer kinetics, but it's not here. I want to start with a simple case. So let me have a look at the other one. Does fast electron transfer mean that the overpotential is zero?
There is a confusion about thermodynamics and kinetics, probably.
No, because the other potential will be determined by my target potential. So if I go back to my slide, sorry, I was trying to think about the question. So I'm starting from the potential EI, where there is no reaction running. You see the current is 0 here. So there is no reaction running on the electrode. And I'm going to, I'm writing a simulation there to step anywhere along this line. So if I step down here, then of course the driving force is very small. But if I step up here, which is what we did yesterday when we stepped directly to EF, the final potential, then here the driving force is very large. So I want to have a simulation that allows me to generate the current transients for any value of the potential.
Perfect. Thank you again.
So carrying on with this simplification, what I do again to show you the mathematics is to make the assumption that the diffusion coefficients are equal, and with that I have a very simple relationship between the species in solution and the starting material. So I can express the product concentration in space and time in terms of the reactant concentrations in space and time. So I can now substitute for the product concentration, for the surface concentration of the product in the Nernst equation. So I can replace the concentration of the oxidized form, which is the product, in the numerator. So now I have an expression between the potential and only the concentration of the reactant. And so I can now rearrange that, and instead of expressing the potential as a function of the surface concentration, I'm now going to, I have done the rearrangement for you here, but it's fairly trivial. I've expressed the surface concentration of the reactant as a function of time in terms of the electrode potential. So at the moment, I'm going to hold the electrode potential at a particular value. So this will be independent of time. Therefore, this surface concentration will be independent of time. Later on, when I will introduce cyclic voltammetry, I will make the electrode potential a linear function of time. And therefore, we will have a dependence of the surface concentration of the reactant on time. But at the moment, we're just doing a very simple experiment. We step the potential to a particular value, and we hold it there. So that determines a single value of the surface concentration. Now, I could, I don't have to make this assumption. I could find an expression for the surface concentration of the reactant and the product, but this is a bit more complicated, and I will show you later on how we can do that. Yesterday I showed you that it was very convenient to express our variables in terms of dimensionless quantities, and we do this by normalizing. So same as yesterday, I'm going to normalize by the concentration of the reactant in the bulk. For the distance, I'm going to normalize by a diffusion layer thickness, delta. The diffusion layer thickness is determined by a particular time, a characteristic time for my experiment, which could be, for example, the end time, the time at the end of my chronoamperogram. And I'm using this time tau to normalize the real time. So concentration, distance, and time are dimensionless. If I implement these dimensionless quantities, I can express the current in dimensionless form, psi. So it's a gradient at the electrode surface. And I showed you there are different ways of expressing it, but actually it's the same. So compared to yesterday, all this is the same. What is new today is, because I want to start to play with the electrode potential, I'm going to express a dimensionless potential. And I'm calling it epsilon. And a very convenient way of doing it is by taking what is in this exponential term here. So by taking the argument of the exponential as a dimensionless quantity, this I can call my dimensionless potential. You will find this in many research articles. It's not just in simulations that people do this. This idea of using dimensionless quantities is quite common in electrochemistry. And it's a good skill to have as well. So I would encourage you to learn to rewrite your expressions in terms of dimensionless quantities. So in the problem in dimensionless form is now a little bit simpler, because I just need one concentration, which is that for the reactant. So this is my transport equation, so fixed second law of diffusion in dimensionless form. This is my initial condition. This is the boundary condition on the electrode surface. So I now have a very simple relationship to calculate the surface concentration of the reactant. This is the expression to calculate the current. And this is the bulk condition, the boundary condition in the bulk, which is the same, as you can see, as the initial condition. So compared to yesterday, this is the only difference. A new expression for the surface concentration. So I hope you can see already that changing the model to simulate one problem or another, actually, most of the time, it involves rewriting the boundary condition. You can keep a lot of the same, you can keep the rest of the model the same, because most of the time it doesn't change. So how does it look like in terms of the algorithm? So if you wanted to write code, well, you do the same as what we did yesterday. You choose lambda, you choose Kmax, which is the maximum number of iteration in time. You choose Imax, which is the maximum number of space points away from the electrode. You calculate Imax from Kmax, you calculate delta T, you calculate delta X. All these things derive from these two quantities, okay? Same as yesterday. You create the arrays for the concentration, and then you set the initial condition for the concentration, same as yesterday. And then you start your time loop. So you now iterate your time using the index K. And the first thing you do is you set the electrode boundary conditions. So this is the new thing. This is where you're going to implement the fact that the surface concentration is a function of the electrode potential. Yesterday, when we were simply simulating the control equation, we just said that C at the surface is equal to 0, because the potential with the driving force was so large that the reactant was totally consumed at the electrode surface. Today, we want to be able to vary that. So this is where we implement the boundary condition as a function of potential. You then carry on with the rest the same as before. You implement the bulk condition. You start your space loop, which is where you really calculate the explicit finite difference scheme. So this is where you calculate the new concentrations knowing the old ones. You calculate your current, you finish the space loop, you finish the time loop, and that's the end of the simulation. So this is the new part. So I'm moving on to another example, but it starts from this simulation. And in fact, this is what you would end up with. So these are current transients, so dimensionless simulated current, dimensionless time. And what you see here is a family of chronoamperograms that have been simulated for different potential steps. So the different potential targets were here. DLE stands for dimensionless potential. So it's the epsilon that I was using before. So for a very large, a large epsilon, I've got the dark blue chronoamperogram, which is right up here. For a smaller epsilon, but still large, I've got another chronoamperogram, which is exactly on top of the previous one. And this is no surprise, because both of these correspond to the plateau of the voltammogram. So I'm still on the pure diffusion control. So in both cases, the surface concentration is still driven to 0. And so I can't see any difference on the chronoamperogram. In this case, in the yellow case, now the driving force is lower. And you can see that the current is smaller. The current is smaller, and it's got the same shape, but the magnitude of the current is smaller. If I drop again the driving force to a lower target potential, I'm seeing exactly the same shape, but the magnitude of the current is different again. And if I make the the target potential even smaller, I have another current transient with lower magnitude of current. And if I even apply a very, very low overpotential, then if I were to zoom on this chronoamperogram, the brown one, it would have the same shape as the others, but the magnitude of the current is smaller. So this is what you can generate with the simple voltammogram that, simulation that I've shown you before. And so with this very simple code, you've got a way of generating any current transient for any potential target within that potential window. What I want to show you with this simulation is how you can simulate what are called sampled current voltammograms. So it's a technique which is very old, but hardly any, barely used nowadays. It's called sampled current voltammetry, and it works like this. You perform chronoamperograms for a series of potential steps, so as I've shown you here, but now what you do is you sample the current at a particular time. So for the one in pink here, so this is the simulated current, and this is now the dimensionless target potential. The one in pink was recorded at, or sampled at, a dimensionless time of 0.1. So if I go here at 0.1 and I sample the current here, there, and here and there, and I plot the current sampled at that particular time according to the target potential, I get a sigmoidal shape, which is called a sampled current voltammogram. If I instead sample at 0.01, so we are very, very close, we are right there. If I sample here and I plot the current sampled there according to the target potential, then I get another sample current voltammogram, which obviously has the same shape, because it's still diffusion control, so it's purely controlled by mass transport. It's got the same shape, but now the current magnitude is much, much larger because it's been sampled at much shorter times. So why is this technique quite useful? Well, it's very nice. Again, from a learning point of view, I like it a lot, but we have used it in research, and it's got some very interesting applications. But if I just show you why I like it as a teaching tool, it's because when you perform your chronoamperograms, you're just getting the rate curves, right? So I've shown you that the rate curves are changing, so we can see it particularly down here. Current as a function of time, the magnitude is changing with the target potential, but you don't see much what's going on. But if you look at it in terms of a sample current voltammogram, you get the green lines. These are the reconstructed voltammograms obtained by sampling the current at a particular time. And you can see that if you sample at very, very short times, you get bigger and bigger currents. But what I like about this simulation and this particular technique is the representation, or if you want, the dependence of the current on time and potential. So it's a very useful plot to really understand the link between the driving force, in this case, the potential, the rate of the reaction, in this case, the current, and how that rate is changing with time. So it's just a very simple simulation to show you some really important relationship between current, time, and potential. Now here, there is no kinetic limitation because I have assumed that the electron transfer was extremely fast, but I could do exactly the same simulation with electron transfer kinetic. And we could reveal kinetic limitations at very, very short times, and then the evolution of the current towards something which is purely diffusion control at very long times. And we have exploited that in our research to compare the shape of sample current voltammograms on microdisc electrodes, for example. So now I want to take this example and I want to make it a little bit more complicated, because I want to simulate situations where the potential is changing with time. So that means during the simulation, my boundary condition will be evolving with time. Why do I want to do that? Well, because I want to simulate a cyclic voltammogram. So I want to be able to ramp the potential between two values and then come back. So I need to be able to implement a boundary condition on the electrode surface, which is now a function of time. And I could do that if I wanted to do other techniques, not just cyclic voltammetry, okay? But the principle is the same. So essentially everything will remain the same, but what I need to do is to implement a condition on the electrode, which is a function of time. So we've seen how we can change the potential. Now we need to do that, but as a function of time. So the algorithm to change the potential as a function of time is exactly the same. So all this is the same as before. The only thing which changes is this bit in red, where you now say that the surface concentration is going to be a function of the iteration value k. So if I put a potential which is changing linearly with time, that means with k, then I will be able to simulate a voltammogram. The rest of the algorithm remains the same. So with this, if whatever the function I put here, I can simulate time-dependent boundary conditions. So let's see how that works. So the first example is very simple. I impose the potential for the first half of the experiment to, for example, drive zero surface concentration. And then for the second half of the experiment, I revert the potential to the original value. And I want to simulate what is known as double potential step chronoamperometry, which is a kind of generation collection technique. So it's very simple. You just say that the surface concentration is constant for half your experiment, and then for the other half, you revert the surface concentration to its original value, which was the initial condition. And that's going to simulate like a potential step on the way forward, and then halfway down the simulation, a potential step on the way to return to the initial condition. And what I'm expecting is something like this. So first half of the simulation, we've got a current transient, which is the Cottrell equation. And then halfway through the simulation, we change the potential to go back to the original value. You can see that the current is changing sign. So for example, you were doing an oxidation on the first half of the experiment, you revert the potential, you're now reducing what the product, and you have a negative current, and you can see this characteristic double pulse, and that's very easily simulated. What you get from the simulation is also the concentration profiles, which I've drawn here for you, and I've numbered them. So you can see from point 1 to point 10, these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are the concentration profiles I was showing you earlier, yesterday and earlier today. And then I want to show you 11, 12, 20. So from 10, which is here, we've got 11, which has this shape now. And then 12, 13, 14, 15, etc., 20. Now, there's a question for you. You can put the answer in the chat. Can somebody tell me why the current is negative after 10? Okay, you can put the answer in the chat. I will carry on my lecture, and then when you put the answers in the chat, I'll stop and come back to that. But have a good look at this figure, in particular at the concentration profiles, and see if you can tell me why the current is negative. Well, similar question: why is the current positive for the first half of the experiment? And why is the current negative for the second half of the experiment? It's the same answer, but be interested to see if you can come up with the reaction changes from forward to backward. Yeah, of course, yeah, but that does not answer. For example, how can I tell from my concentration profiles that the currents on the way forward are all positive, whereas the currents on the second half of the experiment are all negative? Initial slope. Yeah, you're getting there, but I need a little bit more information. What's special about that slope? And somebody give me the most important part of that slope. Of course, the slope is the magnitude of the current, but I'm particularly interested in why the current is negative here, positive in the first half and negative in the second half. Now, there's no convection. My simulation assumes that everything is diffusion control. Okay, if you can tell, because if we go back and we look at the equation that I'm simulating, it's fixed second law of diffusion. There is no convection term here. We're going to see that tomorrow when we do finite elements. So my simulation is purely diffusion control. So there can't be any convection. V equals IR, that doesn't, V equals IR, Ohm's law, no, that's not doing it. Declining slope for second part. Yeah, well, I could argue that my slope are declining, all the slopes are declining. These are declining, right? But that doesn't tell me about why the current is positive. Concentration increases with X for first half and opposite for second half. Okay, we're getting there. We're getting there. Okay, so let me give you the proper answer. You see, the current is proportional to the gradient, and here the gradient is positive. Because on the way forward, I'm consuming the reactant. So although the gradient is actually dropping as a function of time, here it's very steep, here is less steep. So I can see that my gradient is decreasing, but it's a positive gradient because the concentration is increasing as I go from left to right. So as a result of that, my current is positive. When I do the second step, you look at the concentration profiles, and they are very steep here, so the current is very large, but it's negative because here the concentration is decreasing as I go from the electrode towards the bulk. So the concentration is decreasing as I go towards positive X, and then the gradient is, the magnitude of the gradient is decreasing. So we've got a smaller current here, smaller, 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 and smaller and smaller, but they are still negative because the gradient is still going down as I go from left to right. Okay, so what is very useful with simulations is to use the concentration profiles to predict not only the magnitude of the current, but also the sign of the current. So that's why I like simulations because they help me understand. A lot of people just focus on crunching numbers and getting numbers out of simulations. What I like to do is understand what's going on in my experiment. Afterwards, I'll try and get some numbers out of that. But at the moment, I'm not trying to get numbers. I'm just trying to understand why the current has a particular sign and why the current is dropping and why the current is dropping, but in the opposite direction. You see, that's what I like about the simulation. So what we can do with the concentration profile is not only understand the magnitude of the current, but also the sign of the current. And it's a bit the same. You saw the voltammetry before with Mauro. On the forward sweep, I will show you that in a second when we do the simulation. You will see it's a reversal technique. This is called reversal technique. You are reversing the potential halfway through the experiment. In cyclic voltammetry, you are reversing the sweep halfway through the experiment. The concentration profiles, we can use them to understand the magnitude and the sign of the current. So we'll do this again when we do the voltammetry. Okay, so this is where I want to implement a situation where my surface concentration is now changing as a function of time, because my electrode potential will be changing as a function of time. So I want to simulate this very simple voltammogram, the duck shape that we get when we sweep the potential linearly. And I'm going to assume planar diffusion, so it's just diffusion perpendicular to the electrode. And I'm going to assume once again that the electron transfer kinetics is extremely fast, so that the whole current, at least over the range of scan rates I'm going to select, the current will be completely diffusion controlled. So, whereas before I was doing potential stats, I would control the duration of my experiment by saying when to stop, by selecting the time when to stop. In cyclic voltammetry, we control the time scale in a very different way. We don't tell the system when to stop, we simply select a scan rate. So the time scale of the experiment, you can look at it in two ways. You can estimate it by taking the potential difference between the initial and final potential and dividing by the scan rate. So I've got volts divided by volts per second. So this is seconds. So this has unit of time. So this is a characteristic time scale of my experiment. Even if I do one sweep, two sweeps, many sweeps, it doesn't matter. I've identified a characteristic time scale on this experiment, and it's defined by the scan rate. Another way of defining the time scale of a voltammogram is by taking RT over F, and you can check if you want as homework. You can plug in the units. R is in joules per Kelvin per mole. T is the temperature is in Kelvin. The Faraday constant is in coulombs per mole. You can check that this has units of volts. So when you divide volts by volts per second, again, you end up with something which is a characteristic time for your voltammogram. That's something I'm going to use to create a dimensionless quantity. So this is the problem that we want to simulate. We've got our transport equations. Again, fixed second law of diffusion. I've got the initial condition. I've got the Nernst equation on the electrode surface, which relates the electrode potential to the surface concentration. So that is the same as before. What is new is this, a new expression, which is simply a linear relationship between the potential and time through the scan rate. For the forward scan, I've got a plus here. For the reverse scan, I've got a minus. And of course, I need to tell the system that at some point you reach the end of the first scan, you will have to change the sign of the scan rate to initiate the reverse scan. The other expressions are the same. So equal and opposite fluxes for the reactant and the product. This one is to calculate the current, same as before. and then far away in the bulk, we retrieve the initial condition. So you can see that compared to the previous simulation, the only thing that I need to do is to add a line or two of code to implement the linear sweep and then change the sign of the scan rate at the end of the first sweep. So that's the only new thing. So going back to dimensionless quantities, I will use the same for the concentrations. If I want to use two different species, I will use the this ratio of diffusion coefficients. For the distance, I will be using the same expression, which is the diffusion layer is related to the characteristic time of my experiment. But this is the bit which I've just mentioned. We're going to define this characteristic time in terms of how long it takes to go from at the beginning of the scan to the end of the scan. So this will define the duration of one scan. I'm going to use that to normalize the time. I'm going to use this characteristic time to define the corresponding diffusion layer thickness, and that diffusion layer thickness, I'm going to use it to normalize the distance. So to get the expression for the dimensionless current, I have now two more expressions, because this is what we saw before, but now tau is a function of nu, so I can actually rewrite my current in terms of nu, or if I write it like this, you can relate your dimensionless current to the square root of the scan rate. And that should ring a bell to you, because in the previous presentation by Mauro, he showed you that the current on the voltammogram is proportional to the square root of the scan rate. And this is the good thing about the dimensionless quantities. They make appear these dependencies. I've not even simulated anything yet, and I'm already able to show you that the current should be related to the square root of the scan rate simply by manipulating the relevant quantities. I've got here the dimensionless potential, but now I will be sweeping from the initial potential to a final potential. So I have to define a dimensionless initial potential and a dimensionless final potential, but otherwise it's the same as before. So moving on. What about the potential sweep? Because that's the new part in the simulation. So we've got Kmax time iterations during one scan. So that's going to allow me to define a potential increment. So I take the total potential window, I divide by Kmax, and that gives me the magnitude of the potential increment. I can convert that and make it dimensionless in terms of delta epsilon, and it's going to be this quantity in dimensionless form. So I can therefore write a linear relationship between the dimensionless potential starting from the dimensionless initial potential and incrementing by delta epsilon for each time iteration. I need to put a test somewhere in my simulation to say, right, okay, when you get to the end of the potential window, you now need to change the sign of this linear relationship so that we're now decrementing, and we will generate that way the reverse sweep. But it's a very simple piece of code to write. It's just a test. So what I want to do now is to show you how we can do that, but this time include the two species. Until now, I've made the assumption that the species share the same diffusion coefficient, and that allowed me to simplify my model and only account for one species. But now I want to account for the fact that I'm no longer assuming that they have the same diffusion coefficient. This is reasonable because in reality, the difference in diffusion coefficient can be quite sometimes significant. So for example, if you take ferrocyanide, it has a diffusion coefficient of about 0.6 × 10⁻⁵ centimeters squared per second. 0.63 actually, and then ferricyanide, which will be the product in this case, has a diffusion coefficient of 0.72, 10 to the minus 5 centimeter square per second. So 0.63 versus 0.72. As a result of this difference, the concentration profile and the flux are not quite the same. So if you really want to do an accurate simulation, you need to build in your model the fact that the diffusion coefficients can be different. But if you've never done any simulations, then it's good to start from this very simple assumption. And then, as I said in my lecture yesterday, build complexity as you go along, but don't start with a real difficult problem. So now we're going to have to deal with two species. So we'll have to solve two diffusion equations. So fixed second law of diffusion now for two species. So the problem in terms of computer requirement will double if you want, because you now have to construct concentration profiles for two species. That means you need matrices for two species. There will be now two initial conditions. We've got here our Nernstian relationship, but we have now to somehow work with two surface concentrations. We've got the ramp for the potential, forward ramp and reverse ramp. We have to account now for equal and opposite fluxes. Until now, we sort of neglected that. It was dealt with by the assumption that dO was equal to dr. Calculating the current will be the same, and we will have to implement the bulk condition, which will be the same as the initial condition. Does your boundary condition at x equals 0 need to change so the current is dO/CO or just add minus? No, the current is still defined in terms of one species. Here I've chosen the reactant, but what I will need to do is mathematically, we now have a problem because I have two surface concentrations. I therefore need two expressions to solve for these values. And fortunately, we have two conditions. This is the Nernst equation, which relates the potential to these two surface concentrations. And the other condition that we have on the electrode is not in terms of surface concentrations, it's in terms of flux at the electrode surface. So this is condition number one, this is condition number two. We have two relationships. Okay, they're not trivial, but we have two relationships with two unknowns. Mathematically, we can rearrange all that to end up with solutions for the surface concentrations for both species and be able to compute the whole problem. So I don't need to change my the way I calculate the current, but I will show you we need to somehow do a bit of arithmetics to express the surface concentrations using this condition and this condition. Now, we're going to have to pay attention to the value of lambda. I will show you that. Fluxes, I've already mentioned that. And of course, we're going to have to introduce some new dimensionless terms. So in dimensionless form, I now have two diffusion equations, one for the reactant, one for the product. But the fact that we've normalized everything with respect to species R means that we have this ratio here, which is dO over dr. Initial condition is very simple. We've got our dimensionless Nernst equation, if you want. This is the dimensionless linear ramp of potential. This dimensionless equal and opposite fluxes. This is the way to calculate the current. And we've got our bulk boundary condition. So this is what I was saying before. We have two surface concentrations, these two. So we have two unknowns. So we need to somehow combine two relationships. The first relationship will be the Nernst equation, and we'll somehow need to combine that with this one. Two unknowns, two relationships, we can solve it, and therefore we can find an expression for the for each surface concentration and use them in our codes. So I won't go through the details, but it's done here. So the beginning is just writing the diffusion equation in discrete form for R and O. Notice here is an example where instead of writing K plus 1 and K, I'm using K and K minus 1. This is what I was telling you earlier, that you can calculate the future using the present, or you can calculate the present using the past. It doesn't really matter. Here, I've just chosen to write it to calculate the present from the past. So calculate the concentration at K from the concentration at K minus 1. But this is the explicit finite difference scheme for the reactant, and this is the explicit finite difference scheme for the product. Notice that because I've normalized with respect to the reactant, I've got this delta OR, which is du over dr. Okay. Initial condition, well, there's nothing strange here. So this is where we manipulate the boundary conditions to find expressions for each concentration. So the first surface concentration is very simple. You reorganize the Nernst equation and you express the surface concentration of O at time K in terms of the surface concentration of R at time K and potential K. So this is epsilon K. So you can see the relationship with the potential there. But now you need to substitute for that in the second expression, which is equal in opposite fluxes. And then you can rearrange and you end up with this expression for the surface concentration of the second species, the reactant. And so now I've got an expression to calculate the surface concentration of the product, an expression to calculate the surface concentration of the reactant, so I can proceed. If you look, the variables there on the right, we've got the concentration of the reactant, not at the electrode surface, but just after the electrode surface, concentration of the product just after the electrode surface, both at time K, and we've got the potential at time K. So we've got two expressions, so we can now implement these as our boundary conditions, and we can write our computer code. The current is calculated in the same way. It's the gradient right next to the electrode. These are the bulk conditions. So in programming form, we implement the initial condition for both species. So that's initialization of the matrices, if you want. We've got to calculate the potential as a function of the time. So this is our linear ramp. This is our expression to calculate the surface concentration of the reactant using this is where, if you look, if I go back, you see here, it's all in terms of K, K, and K. But really, I want the concentration from something that I know, but I don't know this because that has yet to be computed. So I need to use the K minus 1 value. So in the next slide, I'm rewriting this expression. I keep K on the left, but I use K minus 1 here and there because I know the previous concentrations. So this is what I'm talking about here. This is the new surface concentration for the reactant, and it's in terms of the previous concentration. So the concentration profile that was worked out the time before. So that's why we got K minus 1 and K minus 1. I can still use the new value of the potential, so epsilon K here. And I can do the same for the product because having calculated that, I can plug it here. I can use the current potential value, so at time K, to calculate the new surface concentration. So this is where different numerical schemes would treat this particular problem in different ways, but this is just a very simple way where basically when you don't have a value that you want, you go and use the one that you had before. So you make an approximation, and the approximation is that the values we had before probably are not that different to the value that we are trying to compute now. So this is where we can swap between what you know and what you don't know. But as I said, there are numerical schemes which are far better in that respect. So the bulk boundary condition is the same. You just maintaining the initial condition far away in the bulk. So now we have two discretized fixed second law of diffusion. So we've got the explicit finite difference scheme for the reactant. So this is exactly what we saw yesterday. But now I've got a new one, which is for the product. And it looks exactly the same, but we have this new term which reflects the fact that the diffusion coefficient of O is not the same as the diffusion coefficient of R. So this is going to be important because yesterday I told you that we had to have a constraint on the value of lambda, which was delta T over delta X squared. Well, now we need to account not just for delta T over delta X squared, but we need to account for that. And it's this quantity here which needs to be less than 0.5. So yeah, so I've already talked about the difference between K and K minus 1 here. And this is what I was saying. So now we've got lambda here, and here we've got this product, which is lambda times delta or R. And this is what needs to be less than 0.5. So I can move on. So this is focusing on the constraint. Yesterday I showed you that lambda couldn't be, had to be smaller than half. Well, now it's this quantity that needs to be smaller than half. So I suggested that you should use 0.45. Well, in that case, you must make sure that this is not greater than 0.45. So that's a little bit of a constraint, which is inherent to this particular numerical scheme. And as I said, there are other numerical schemes that don't have these constraints, but the explicit finite difference is sufficiently powerful that it's well worth using. So when you run the simulation, this is what you produce. So this links to what Mauro was showing you before. But what I've done here is to simulate the concentration profiles and to number them so that you can see where they are on the voltammogram. So in red, we have the concentration profiles for the reactant. In black is the product. And I've just done the product for one time. In blue, we have the concentration profiles for the reactant, but for the reverse sweep. So in red is the forward sweep. In blue, it's for the reverse sweep. So let's focus on the evolution of the concentration profile in for the reactant on the forward sweep. So I've got them numbered as 1, 2, 3, 4, 5, 6, 7, 8. So you can see 1 here. Well, it's right there. And the reason the current is very, very, very small is because if you look at this gradient, it's virtually flat. So if the gradient is virtually flat, that means there is very, very little flux. So if there is a very small flux, there must be a very small current. At 2, you see the current has increased a little bit. So 1, 2, 3, 4, 5, 6, 7, 8. So at 2, we are there. And so we can see there's a little bit of a current, and that's because there is a little bit of a gradient. At 3, the gradient is steeper. So I can see that we are now rising on the voltammogram. At 4, we are here. At 5, we are there. Okay, but not quite at 0. 0 is down here. So 5, we're not quite at 0, but we have started to begin the decay of the current. Now, could somebody tell me why? What is the dependence of the current on time in this region? At the moment, it's plotted as a function of potential because it's a voltammogram, but remember, the potential is a linear function of time. So I could consider this as a time-dependent current. So could somebody tell me what is the relationship between current and time in this region? At 6, you can put that in the chat while I carry on talking. At 6, we are down there, but not quite at 0. 7 and 8, we are down there at 0 surface concentration. At 8, we turn around and we begin the reverse sweep. So we get to 0.9 down here, 0.10, 0.11, 0.12, 13, 14, and 15. So this is reminiscent of the concentration profile that we saw when we simulated the double potential step. And it's another example of what we call a reversal technique, where you do something on the way forward, then you reverse your action on the way back. And you can see that the impact of this reversal in the perturbation waveform is to bend the shape of the concentration profiles. Here, the concentration profiles are drawn towards the bulk of the solution by diffusion over time. When you reverse the perturbation, now they are returning, the surface concentration you can see is returning to the initial value, which is the initial condition. And you can see that this creates a trough in the concentration profile away from the electrode. And that trough is very close to the electrode at the beginning. And with time, that trough is moving away from the electrode surface. So, nobody come up with an answer? Very good. Excellent. The current is proportional to the 1 over the square root of time. And the reason is that when your surface concentration is more or less 0, what's happening here is pure diffusion. So it's like having done a potential step to this value, and then you're just watching your concentration profile just being drawn and drawn further into solution. So this is like the Cottrell equation in a way. Your current is related to 1 over the square root of time. Very good. Now another question for you. Can somebody tell me why the current is 0 at this point here? Or another question, the same question, but put in a different way. What would be the shape of the concentration profile close to the electrode at this point, when the current is crossing the 0 current axis? And this relates to the question that I asked earlier about the magnitude and the sign of the current. Very good. Excellent. And you can see that I didn't draw it. You can see that, but if I had drawn a point between, say, 11 and 12, exactly at the crossover here, what you would have seen is that the current, the concentration profile at that point would be horizontal. When the concentration profile is horizontal, that tells you that the flux is 0 because your gradient is 0. So when the gradient is like this, we get positive current, 0, negative current. So at that particular point, the current is changing sign. So it's positive here because the gradient is still like this. Then it crosses, it's 0, and then the gradient becomes negative. The current becomes negative because the gradient is negative. Again, another example about the use of the simulation to really understand what's going on in your experiment. Then I could ask you the same question here. Now we are pinning the surface concentration back to 1, the initial condition. And as a result of that, it's like having a potential step. The current, the surface concentration is not changing, but the current is simply a function of 1 over the square root of time. Okay, now I want to move to something even more interesting, and this is how to account for kinetics, electron transfer kinetics. So until now, I've just focused on simulations where we accounted for mass transport, but we have assumed that there was no electron transfer kinetic at that point, or rather, we have assumed that the electron transfer kinetics was extremely fast. Now I want to build in my simulation the possibility that there is finite rate of electron transfer for the conversion of the reactant into the product and for the conversion of the product back into the reactant. So what I'm going to do now is to write the current as a sum of two terms. A term where we've got rate constant times the surface concentration of the the reactant. So this will be a current term which represents the rate of the oxidation of R. And then, because this will be the reverse reaction, there's a minus here, we have minus the rate of the conversion of the product back into the reactant. And this is now with a different rate constant. This one is the rate constant for the reaction in that direction, Kr, and this is the rate constant for the reaction in this direction back to R, so Kf. Now I've made these rate constant time dependent because I want to be able to simulate the voltammetry, so I want to simulate the role of the potential sweep. And so what I'm going to do is find expressions for Kf and Kr. And to do that, I'm going to make very simple assumption that the electron transfer kinetics follows Butler-Volmer kinetics. And I'm going to express these rate constants in terms of two variables. One is the standard rate constant for electron transfer, K0, and the other one is the transfer coefficient alpha. This is the E0 for the redox couple, and the potential will be a function of time because I'm obviously sweeping the potential during the voltammogram. So Kf and Kr are a function of time because the potential is a function of time. So now putting all this together gives me this expression for the current. So I've got the rate constant, the standard rate constant for electron transfer, a term which reflects the forward reaction, the oxidation of R, and then another term which will correspond to the reduction of O, so the consumption of the product by the electrode surface. And this will be a function of potential, this will be a function of potential, therefore both of these terms will depend on the potential scan rate and potential run. And we have the transfer coefficient in both cases. So what I need to do now is to implement this in my simulation. So in dimensional form, I've got my diffusion equations, I've got the initial condition, I've got equal and opposite fluxes because this has to remain. And now, instead of using the Nernst equation to make a relationship between the electrode potential and the surface concentrations, what I have is a link between the gradient, which is related to the current. So this is the gradient of the reactant. And now I have this complicated expression, which is essentially taking into account the kinetics of the forward process and the kinetics of the reverse process. I need to obviously implement the linear ramp. So here it is for the forward scan and for the reverse scan. And then we've got the bulk condition. So we're back into the situation where we have two species. So we need two constraints. One is this one, equal and opposite fluxes. And the second is this one, where the flux of the reactant is related to this kinetic expression for the current. We have two equations, therefore, for two species, therefore we can solve that, and we can come up with a mathematical expression that will allow us to define the boundary condition on the electrode surface. The rest remains the same, as I explained before. So in dimensionless form, okay, question. Can you please show what boundary condition the Butler-Volmer replaces? Okay, let me go one step back. Before we have, okay, let me put it in the dimensional quantities. Before we had equal and opposite fluxes, and the Nernst equation. These were our two constraints. We had two constraints, two species. We could solve for the, we could find a mathematical expression for the surface concentrations, and we could run the simulation. Now, this is still there, but this is no longer in the boundary condition because I'm not assuming equilibrium. Instead, I'm assuming Butler-Volmer kinetics. So this is where it goes. So I retain the equal in opposite fluxes because this is always there, but I've replaced the Nernst equation with this long expression for the flux, relating the flux of the product with the electron transfer kinetics. That's the only difference. This is the new bit. This expression replaces the Nernst equation. So I want to make this dimensionless. So I use the same expressions to make my model dimensionless. So diffusion equation for R, diffusion equation for O, initial condition for R and for O, equal in opposite fluxes. What's different now is we've got this expression in terms of the kinetic term. And this is where I need to introduce a dimensionless rate constant for electron transfer. And we do it. So K0 is in centimeter per second. You multiply by the characteristic length, which is here, the diffusion layer, and you divide by the diffusion coefficient. So centimeter per second multiplied by centimeters divided by centimeter square per second. This is dimensionless. Another way of looking at it is that way. It's fine. As well. So I'm going to be using this dimensionless rate constant for electron transfer because it's a very powerful term. And the reason I define that quantity is because when you regroup all the variables, you end up with this expression here in front of the big term there, and this is dimensionless. So this is a convenient expression to turn into a dimensionless electron transfer rate constant. Okay, the rest is the same: dimensionless linear ramp, and then dimensionless. No, K0 is not the exchange current density because the exchange current density would be NF. So number of electrons times F times the area of the electrode times K0, which would be the standard rate constant for electron transfer, times the concentration that you have in the system. Okay, so big K0 is dimensionless, so it cannot be a current density. A current density would be ampere per unit area. This has no unit, so it is definitely dimensionless. But K0 is, you see, there is no unit of current here. It's purely distance and time. Okay, so K0 is definitely related to the standard rate constant for electron transfer. You can calculate the exchange current density from the standard rate constant from electron transfer, but the big K0 here is not the exchange current density. So bear in mind this quantity because we're going to be using it when we run the simulation. So it gets more complicated again. It's simply this region again. It's how to implement the boundary condition. The rest is all the same. We haven't changed that, but we have to somehow express these constraints. So this is equal in opposite fluxes, and this is the flux of R being related to the kinetics of the electron transfer process. So we've got now, when you look at it, we've got two equations, but we have four unknowns. We have CR at the electrode surface at time K, CO at the electrode surface at time K, CR, the first point in solution at time K, and O, the concentration of O in the first point in solution at times K. So this is 4 unknowns in the way I've written it here. So what we're going to do, as we did before, is we're going to be using to end up with two equations and 2 unknowns. What we're going to be doing is we're going to be replacing some of the quantities with the values that we had calculated at the previous time iteration. So we will produce a system of 2 equations and 2 unknowns simply by replacing these 2 quantities these with the values at k-1, which are known because we have computed them at the previous iteration. So again, it's a little bit of arithmetic to substitute an estimate for a value that you don't know. And very often you take the estimate from the previous iteration because it's been computed. Therefore, that value cannot be very far from the one that you are trying to use. Of course, this only works if your time increment is very small and if your space increment is very small. So that's why I said that the convergence and the resolution of this of the simulation really depend on how many increments you have, both in space and time. This concept will come back tomorrow when we talk about meshing in finite element, and it's general really. Every numerical scheme depends on the quality of the mesh. And here, because we are solving a partial differential equation, we have a mesh in space for the concentration away from the electrode, but we also have a mesh in time because we want to simulate the evolution of the concentration. So if you make big steps in time, then it becomes very difficult to accurately calculate the changes in the concentration. Does replacing K with K1 requires any constraint on the variation of potential variation during? No. Any constraint on the variation of potential variation during time K and K1? No. We can still live, I don't know if I've put it on the next slide, but we can live, we can keep the potential at K. But I could use the potential at k-1 as well. It would make a slight difference, but it's all to do with how small a mesh you're using in space and time, basically. Okay. I don't think it makes a difference whether you use k-1 for the potential or K for the potential. I don't think it makes a difference. It might make a small difference, but it's not. It's in the noise, I think. So I have gone through the whole mathematical treatment of this problem, and I show you the expression that you come up with for the surface concentration of the reactant and then the surface concentration of the product. As you can see, it's k-1 for the concentrations, k-1, k-1, and then K, and K for the potential. So essentially, I've kept the potential at time K, but I've used estimates of the concentrations by taking the previous values. So that allows us to produce 2 expressions for 2 unknowns, and now we can run this simulation. The bulk concentration, the bulk condition is the same, initial condition is the same, and the ramp is the same. So let's see what we get from that. Oh yeah, well, these are the diffusion equations. So this explicit finite difference scheme for the reactant and the product, that's the same as before. And this is the way to calculate the current from the gradient of the reactant concentration. So these are simulations, 4 different simulations, which I made using this algorithm. And I've done them for 4 different values of K0. So if you look the dark blue here, so it's a dimensionless current, dimensionless potential, okay? And in the dark blue here, we have a very large value of K0. So since K0, let me go back to remind you what K0 stands for. K0 is this, okay? So K0 is proportional to standard rate constant for electron transfer, okay? So what we're seeing here, when the standard rate constant for electron transfer is very, very large, I have a voltammogram which has this shape. It looks very normal to me. And I would check that it is the shape that we normally get for pure diffusion control by looking at the peak potential difference. For one electron transfer process, it should be about 60 millivolts. Okay, so I would look at the peak potential difference, and it would be very, very close to 60 millivolts. I drop by a factor of 10 the value of K0, and now look at the shape of the voltammogram. It's drawn out more to the right. The current has dropped a little bit. The reverse peak is drawn out more to the left. So if I measure the peak potential difference here, it's much bigger. If I drop the rate constant by another factor of 10, you can see that the current has, again, the peak has moved further to the right and this one further to the left. And you can see now there is a region here where there is virtually no current. And if I drop the rate constant by another factor of 10, then there is a region here where there is no current. And now we get a peak very far off to the right compared to this one. Then we turn around, zero current, and then the reverse peak here. So this is an example of what happens when you are recording a voltammogram with a very, very fast redox couple. So it is purely diffusion controlled. And then with a slower, and very, very slow redox couple. Okay. So this is to illustrate that with just a very simple simulation using explicit finite difference, we are able to simulate the shape of the voltammogram and the dependence of the voltammogram and the magnitude of the current, of course, and all that as a function of the rate constant for electron transfer. Now, the other thing we can do with this voltammogram or with this simulation is to consider K0 in a different way. Because if we go back to the slide where, where I define K0, the dimensionless rate constant K0 is a function of tau, square root of tau. And tau is the duration of our sweep for the voltammogram. And that is inversely related to the scan rate. So this K0 is actually for a constant standard rate constant for electron transfer is proportional to 1 over the square root of the scan rate. This is very interesting because in reality, you don't do you would have to observe these 4 voltammograms, you would have to come up with 4 redox couples, a very fast one, a slow one, very slow one, and very, very slow one. Okay, this is not the way it works in reality. What you have in your electrochemical cell is a redox couple, and the parameter that you play with during your experiment is the scan rate. So in other words, you use the scan rate to tune the time scale of your voltammogram with the time scale of the kinetics of the electron transfer process. So you can now look at these voltammograms in terms of different time scales for the same redox couple, therefore for the same standard rate constant for electron transfer. At low scan rate, the electrode is basically waiting for the reactant to arrive. And therefore, the voltammogram is purely diffusion controlled. There is no kinetic information in the blue voltammogram, okay? I could have simulated that voltammogram with the Nernst equation on the boundary condition, and I would get exactly the same thing. In contrast, if I increase the scan rate for the same redox couple and therefore for the same electron transfer kinetic, if I increase the scan rate, I am now shrinking the thickness of the diffusion layer. This is what Mauro was showing you. I shrink the thickness of the diffusion layer, and now I get to a situation where the reactant is arriving really, really fast towards the electrode. And now the electrode is showing kinetic limitation. And we can see that because the peak current has shifted. Sorry, the peak potential has shifted to more positive values. You need a higher driving force to get the same rate. If I increase the scan rate even more, you reveal the kinetic limitations more and more. So this is one of the beauties of dimensionless quantities is that for a single set of voltammograms, you can think of them in two ways, either as changing the magnitude of the electron transfer rate constant for a given scan rate, or more likely, because that's the way we do the experiments generally, you have a given standard rate constant for electron transfer, but you've used these voltammograms as representing increasing scan rates. Now, another reason for using dimensionless quantities is because you know that the current is proportional to the square root of the scan rate. So if these voltammograms had been recorded for different scan rates, the magnitude of the current would be completely different. And that's why it's important to use dimensionless current, because you are normalizing in the dimensionless current. It was one of the expressions I gave you at the start. You are essentially normalizing by the square root of the scan rate. And that allows you to compare the shape of the voltammograms. This is very important in voltammetry. Whenever you suspect mass transport by diffusion, always try to replot your voltammograms according to current divided by the square root of the scan rate. Okay, so I want to move on, and I want to show you how we can take the simulation one step further and include coupled chemical reactions. So I'm only going to take one example, and I know you've seen them with Mauro earlier. You've seen the effect of coupled chemical reactions on the voltammetry. I just want to show you how we can simulate that. So I'm going obviously to have my mass transport for the reactant and the product, but I will also want to include some homogeneous reaction. I'm going to assume that the electrode is not kinetically controlled, so I'm going to make the electron transfer very, very fast. The case I'm going to simulate is what we call the following chemical reaction, where the product of the reaction reacts in solution to form a new species. So this is it. It's called ISE mechanism. So E stands for the electrochemistry step, and C stands for the chemical step. So this is at the electrode surface. This one is in solution. If I just consider this chemical reaction and I write the kinetic terms for this, I will have, very simply, the change of concentration of O with respect to time is minus K times the concentration of O. For the species Y, I will have the change of concentration with respect to time is equal to plus, because it's formed as a product, times the concentration of O. Okay? But this ignores mass transport. In our system, we've got mass transport and chemical reaction. So if we account for mass transport, I now need to account three species, because these two, well, all three are involved in mass transport. Only R is not involved in the chemical reaction. O and Y are both involved, but R isn't. So if you look at the combined reaction diffusion problem, you've got the diffusion equation for R, but no kinetic term, because it's not involved in the chemistry. Whereas for O, we see a consumption here, so a mass transport term, diffusion term, and then a kinetic term. For Y, you get a mass transport term by diffusion plus a kinetic term. So you can see now the complexity is going up. Although we have a very simple scheme, we now need to solve 3 partial differential equations, 1 for each species. This is where you start to need a very efficient, fast numerical scheme. So in dimensional form, you've got 3 partial differential equations, 2 with kinetic terms. You've got now 3 initial conditions, 1 for R, 1 for O, 1 for Y, where generally the product and the 2 products, O and Y, are not present in the solution. Okay, so we set them to 0. I'm assuming very fast electron transfer, so I've reused the Nernst equation for the electrode surface. I want to simulate the voltammetry, so I've got my linear ramp. And now I have another complication. It's to account for what happens at the electrode surface with respect to the Y species, because this is only related to O and R, equal in opposite fluxes, that's only related to O and R, but I also need to account for what's happening with respect to Y. Now, generally, Y is not electroactive. But if it were electroactive, then you would have to make a different boundary condition. Here, I've simply assumed that it's not electroactive. Therefore, its concentration gradient will be 0. So this is one of those cases where the concentration profile of Y will always be perpendicular to the electrode surface. I calculate the current in the same way, and I impose now 3 bulk conditions, 1 for R, 1 for O, and 1 for Y. So that's the problem in dimensional quantities. In programming form, I've stepped one thing. In programming form, we've got 3 initial conditions. We've got the boundary condition at the electrode. So the new one, these 2 we've seen before. The new one I could highlight is this one. This is where the concentration of the Y species at the surface of the electrode is equal to the previous concentration in solution. Previous as in time before, but in solution. This is 0 at the surface, 1 is the first point in solution. And this effectively implements a 0 gradient, and therefore no flux. These are the 3 bulk conditions, and this is where I want to focus. It's the 3 partial differential equations. So for R, we see the same as before. For O, we see the same, and then we have to include kinetic terms. So this is in dimensionless form, and so we've got to account for that. And this comes from rewriting the equations, taking into account all the quantities. K is a dimensionless rate constant for the following chemical reaction. Delta T is the time increment in the simulation, and this is the concentration of the O species in the solution. For the Y species, we now have to create this new equation. So instead of delta OR, we now have delta YR. So we need to be careful that either this one or this one is not equal to, has to be, both of these have to be smaller than 0.5. And we have a new kinetic term, which is positive here because the Y is being produced by the chemical reaction. But we still have delta T, and we have the rate constant for the chemical reaction. The calculated current is the same. So this is, where the complexity goes up, because now we've got 3 partial differential equations, we've got 3 initial conditions, we've got 3 boundary conditions, 3 bulk concentrations, and we have now to be very careful about the changes that have occurred to the partial differential equations. So let's talk about these changes a little bit and focus on the constraints. So I told you that these quantities have to be less than 0.5. This one obviously needs to be less than 0.5. There is a new constraint, is that the value of K delta T shouldn't be too big. Again, otherwise the concentrations will start to oscillate and you end up with negative concentration. So we now have a trade-off between the value of K, the rate constant, and delta T. So if you have a very, very fast following chemical reaction, so if big K is large, then your delta T would need to be very, very small. And essentially, this boils down to what I've explained here. You have to, I mentioned right at the start of my lecture yesterday that we need to take into account different length scales. And I said that when you have a couple chemical reaction, there's a length scale which is the reaction layer, which is the region of space where the reaction takes place. So we have a diffusion layer, which is the region of space in front of the electrode where the diffusion takes place, but we also have a region of space where the chemical reaction takes place. And essentially, you need to make sure that the reaction layer isn't too small, because if it's too small, you won't have enough space points to resolve this very, very fast chemistry. Basically, if the rate constant is very, very fast, the reaction occurs in a very thin layer, and that becomes really difficult to simulate. So you want to make sure that you've got enough discretization within the reaction layer, in the same way that we need enough discretization within the diffusion layer. You need enough discretization within the reaction layer to account for the chemistry which is taking place in the solution. And typically, you need to make sure that you have at least 10 points, spatial points, within the reaction layer to have a reasonable estimate of the effect of the chemistry, the following chemical reaction on the concentration profiles. So this is my last example, but just to say with this simulation, you can produce the voltammograms that Mauro showed you, where the following chemical reaction essentially consumes the reverse peak, because the reactant is being, sorry, the product is being consumed by the following chemical reaction. So you still see the forward peak, but the reverse peak has disappeared because of the following chemical reaction. But if you go really, really fast, and this is what you can do with the simulation, if you crank up the scan rate so that your diffusion layer is very, very, very thin, then you will see your voltammogram as a normal shape. As you lower the scan rate, then you give more and more time to the following chemical reaction to do its job, and then you will see that the shape of the reverse peak will gradually disappear. So I won't show you that, because I've got one more example that I really want to cover. And this is a situation which is very different to what we have seen. It's very simple to simulate, but it starts from a different approach. All the simulations we have covered so far pertain to potential static control. So I was controlling the potential, and therefore I was controlling the surface concentrations. Now I want to simulate the charge of a battery. And here I want to simulate a constant current experiment. So this is galvanostatic control. And if I control the current, I am not going to control the concentrations. I'm actually, the control is on the gradient of the concentration, because the current is related to the gradient. So I'm going to control the flux of reactant or product, but I am not going to control directly the potential. The potential is going to be something, is going to be the signal that we measure. So I will be looking at the value of the surface concentration to retrieve the electrode potential. So I've simplified the problem as much as possible. I'm only considering one electrode. I am considering this is an electrode which is thick. So it's an intercalation problem. I'm going to intercalate, for example, lithium into a composite electrode. So I have to account for the thickness of the electrode. I'm saying that one side of the electrode is electroactive. So that's the side which is in contact with the electrolyte. the other side of the electrode is not electroactive. It could be, for example, the current collector in a battery. I'm going to start with the situation where the electrode is initially empty, and I'm going to charge the electrode, so charge the battery in effect, by loading the redox species inside the electrode from the electrolyte side on the constant current, so on the galvanostatic control. I'm allowing the species to intercalate in the electrode by diffusion. This would be, for example, akin to ambipolar diffusion, where you've got the diffusion of your lithium ions and at the same time the diffusion of the electronic charges in the composite electrode. So it's a diffusion control process that we are simulating. And we're going to stop the simulation when the battery is charged. So you have to decide how to implement that in the simulation. A very simple way of doing it is to monitor the concentration inside the material and stop the simulation when the concentration reaches a particular maximum. To make life easy, we're going to assume that the two species have got equal diffusion coefficients. So I will only have one species to simulate. And so what I want to do is calculate the concentration profile as a function of time inside the electrode during the loading. And I want to calculate how the electrode potential is changing during the loading. And of course, I want to also monitor how much charge has been used to do this. So it's best to look at the model not with equations, but with a schematic. And this is it. We've got on the left-hand side, we've got the solution electrode interface. So the electrolyte is going to arrive from the left. Okay, that's fine. On the right-hand side, we've got the inert wall, which would be, for example, current collector. Okay, this is the thickness of the electrode, L. That's the layer thickness. And this is the region that I want to charge. The insertion is going to occur from the left. So this is where we're going to impose constant current. By constant current, we're going to impose constant gradient. So that means the flux of material will be the same throughout. This is the concentration limit. So whenever the concentration is going to reach this maximum, we're going to stop the simulation. Okay. So this is a very simple example of what could happen, for example, when you're inserting lithium into a composite electrode, or inserting hydrogen into a palladium electrode, for example. It's the simulation of a solid state insertion process, if you want. So in dimensional form, with all the assumptions that I made, I just have one diffusion equation for the species of interest. I don't even call it O or R, it doesn't matter, it's just C for the concentration. Now, you see, the initial condition, I have to restrict it to the thickness of the electrode. So it's only for X between 0 and L. I'll make it 0 because the electrode is initially empty. At the electrode surface, my condition is that the flux is equal to the current, determined by the current. So I'm imposing a gradient this time. Whereas in the previous simulations, we had this the other way around. We were calculating the current from the flux. Now we're calculating the flux from the current that is imposed by the galvanostat. Now the output that I want is the potential. So I'm going to use the Nernst equation. I'm assuming there is no electron transfer kinetic here. I just want to express the potential in terms of the surface concentrations. And the boundary condition on the other electrode, on the other side of the domain, is 0 flux, because the wall is not an electrode, it's just a current collector. So in programming form, it's fairly straightforward to impose a gradient. This is just the forward difference in time, in space rather. But here I mix time as well. And this is the constant current which is imposed, or constant gradient which is imposed. This is the increment in space. This is no flux. on the outer wall, on the inner wall. This is the explicit finite difference scheme, so very simple, same as before. And this is the way to calculate the potential from the surface concentrations. So the model is actually very simple. So we need to think about how to stop the charge. So I said whenever, so you put a test in your simulation and you tell it to stop when a concentration reaches the maximum. This will obviously be dependent on the thickness of the electrode. So you'll be able to play with the value of L. And it will also depend on the charging current. If you put a lot of current on your galvanostat, then of course you're going to charge this very quickly. If you drive your charge with a small current, then it will take much longer. And so how quickly you get the maximum will depend on these conditions. Okay, and the other thing that I want to do is calculate the total charge at the end. So at the point when the simulation is stopped, when you reach the limit, we need to calculate the charge. So how to calculate the charge? Well, it's very simple because you just need to integrate the current. So this is our dimensionless current. You integrate with respect to time, it gives you the charge. In discrete form, it's simply a discrete integral. But because the current is constant, you can take that out and basically you're just summing up the time. So the charge is simply current proportional to time. So the charge is a linear function of time through the current. Okay, very easy to do that in the simulation or in a spreadsheet. Okay, if we have only one species, how do you relate the potential of the electrode surface? I'm sorry, I missed the potential expression in slide 43. I did it by assuming that the two species had equal diffusion coefficients. So I made, I wanted to make it very simple. So I've assumed equal diffusion coefficients. So it's allowed me to rewrite the Nernst equation in terms of one species rather than two. So this is where you calculate the total charge or the maximum charge, because what's interesting is to compare the charge at the end of the charge, when you're fully charged the electrode, or when you reach the stop point, compare that with the maximum charge. But the maximum charge you can calculate without simulation. It's simply Faraday's law. And that's defined by the cell volume and the concentration of the maximum concentration and NF. So you can relate the maximum charge to the input quantities in your simulation. But the interesting thing is to compare the charge at the end of the charge with the maximum charge to see whether the battery was fully charged or not. So with this very simple model, you can predict whether you have fully used the available capacity of the battery when you vary the charging current or the duration of the experiment or the upper concentration limit, which is the Cmax, or even the cell thickness. So it's a really simple model that allows you to simulate how to charge a battery. And you could obviously discharge it by running it in the other way. So this is probably my last slide, and last but one, and it's just the output of that very simple simulation. So what you have on the left-hand side is the concentration. This is the distance, it's all dimensionless. At the beginning, you see a flat concentration profile, but as time goes on, you see that the concentration is increasing on the left-hand side. And of course, diffusion means that the material is diffusing into the electrode. And what you should pay attention to is the gradient here. See, all these gradients have the same value. So all these lines are parallel. The surface concentration is increasing. In fact, I've plotted it here as a function of time. You see the surface concentration is increasing until it reaches its maximum. So that when the surface concentration reaches that point, that's when the simulation will stop, because you've reached the maximum charge at that point. You could stop it in a different way if you wanted. But the other point to look at is this boundary condition. You see, this is the other end of the electrode, and this is the inert wall. And what's happening here is that these gradients, they are all the same. They are flat. And that's because we have a non-reactive wall. So there is no flux here, which means dCdx equals 0. That's the surface concentration, as I mentioned. And what's interesting is if you take that and convert it into potential using the Nernst equation, you get a typical curve as you would obtain for the charge or discharge of a battery. So you see the dimensionless potential is dropping rapidly at the beginning, then not quite constant, but reaching a plateau, and then it stops. It drops very rapidly. So this is a very simple model for how a battery works, or an intercalation material operates. So I think I've spoken for quite a long time. These are my key points. I'll leave you to read that while. Okay. Why is rho equals square root? Where does it come from? Reaction layer thickness, page 38. Can the PDE be simplified by moving the reaction to boundary condition? All right, I'll answer the second question. You don't want to move the reaction on the boundary condition, because that implies that your reaction is so fast that there is no homogeneous process and everything is happening on the electrode surface. Okay, that is not what we're trying to model. So we are trying to model the situation where the product of the electrochemical reaction is able to diffuse in solution, but at the same time react. If you constrain the reaction to be slap bang on the electrode, that's equivalent to having a super fast coupled chemical reaction, and basically your product is totally consumed as soon as it is formed. Okay, so you wouldn't do it that way. Why is there a square root in slide 38? Okay, I'll get to that. Well, again, we are looking at distance here, and the way to estimate a reaction layer, I think in Mauro's lecture, you had a similar concept, which I think he called the Denuault number or something like that. Okay, well, this is the same idea. You have a species, and I'm using delta, the diffusion coefficient of R, because I've been normalizing everything with respect to the reactant. So I will be doing the same here. But you could put DO if you want. You have a characteristic diffusion coefficient, and you have a characteristic rate constant. This will be a first order reaction. Okay, so this will be second to the -1. This is centimeters square per second. So the second to the -1 cancel, you take the square root, and you end up with a distance. This is the characteristic thickness of your reaction layer. This tells you that the chemical reaction will occur over a region equal to the value of rho. I hope that makes sense. But essentially, it's very similar to the Denuault number that you saw with Mauro earlier. Why the root? Because if you don't take the square root, then the units are not consistent with a distance. The diffusion coefficient is in centimeters square, second -1. The rate constant is in second to the -1. So the second to the -1s drop out. You're left with centimeters square. You need to take the square root to get a distance. Okay, so I'll go back to my last slide so you can read the key points while you're putting some questions if you want. Yeah, it is the homogeneous reaction. Yeah. When we're talking about the square root, it's the reaction layer for the homogeneous reaction. So the problem is complicated because you end up with two layers that need to be compared in terms of thickness. you have the diffusion layer, which is how quickly you bring the reactant to the electrode. So this has a particular thickness, which in this case would be determined by the scan rate. So if you use a very, very fast sweep, very high scan rate, you would have a very narrow diffusion layer. If you use a slow sweep, you would have a very large diffusion layer. Okay, that is under your control because you are controlling the waveform generator, therefore you're controlling the scan rate and therefore how long it takes for the experiment to complete. Then there is another layer, which is the reaction layer, and that is determined by the rate constant of that particular chemistry. If you have a very, very fast rate constant, very high rate constant, therefore very fast couple chemical reaction, the reaction layer will be very, very thin and sticking to the electrode, okay? Almost like a skin on the electrode, okay? That will get bigger and bigger and bigger if you have a slow reaction. So when you, the rate constant is determined by the temperature because it's typically an Arrhenius type problem. So for a given temperature, you will have a given reaction layer thickness. So what you can do with your experiments, you can tune the scan rate to explore, essentially what you want to do is you tune the scan rate or you adjust the scan rate to tune the time scale of your voltammogram with the half-life of the product of the reaction. If your experiment is your scan rate is very small, then your diffusion layer is very, very large and everything is consumed and you don't see the back peak. If on the other hand, your scan rate is very, very large, you have a very narrow diffusion layer, your time scale of your experiment is much, much, much shorter than the half-life of the O species. And in that case, your voltammogram looks like the normal duck shape. When you tune the scan rate to be so that your experimental timescale is comparable to the half-life of O, then you have a lot of kinetic information about this couple chemical reaction. Could you explain about the Thomas algorithm to solve tridiagonal matrix? Well, the simple answer is no. That is purely mathematical problem. I don't deal with that. As I said yesterday in the lecture, I would go into MATLAB, I would fish out some numerical solver, I would expect these guys to have optimized the solver. The trick is to choose the correct solver, because if you go into MATLAB, for example, or even in console multiphysics, the same problem occurs. You've got a whole library of solvers. The difficulty for me is to choose the correct solver for the problem in question. With console multiphysics, you will see these guys are charging you because they have already pre-selected some optimum solvers for electrochemical problems. So when you buy their electrochemical module, they will already have used mathematicians who have selected the best solver for the job. If you are solving, I don't know, fluid dynamics, they would propose you different solvers for the job. Your question is purely a mathematical question, and I can't answer it. Sorry. I've read about the Thomas algorithm, but a long, long, long time ago, and I can't remember.
No more questions.
Okay, so the plan for tomorrow is that we're going to take a different approach. we're going to move from finite difference to finite element. And we're going to look at, I won't go into the mathematics anymore because I will be showing you a very different way. I'll be using a solver, a package, and I will show you how we can put together the model within the package. But you will see the parallel with what we've done today and yesterday. You will see that although we're not actually writing equations, we are choosing modules which have the same effect as imposing a boundary condition, imposing an initial condition, imposing a particular PDE, imposing a condition on the electrode or something like that. So there is a very strong parallel with the way I've presented these very simple simulations using the explicit finite difference and the way that COMSOL multiphysics actually approaches the model. So that's what we're going to do tomorrow.
Perfect. Thank you, Guy, for today. The participants are saying thank you to you. It's amazing how you share your knowledge about the simulations. For me, it's great. As I mentioned yesterday, I always learn something new about the simulations, how to use the boundaries, how to put. It's amazing. Thank you very much, Guy. I am waiting so much for tomorrow. Tomorrow will be interesting to see changing the parameters. It will be good. Thank you very much.
Thank you. I love simulations. So
yeah. This is one of the reasons why I love to see your lectures too. The way how to explain the examples is it's amazing for me. It's fascinating. Thank you very much, Guy, for that.
Thank you very much.
And we see at the same time tomorrow. The people are asking in the chat. Same time tomorrow. We will do a lot of more simulations and the Gabriel's lecture. And see you everybody tomorrow. Thank you again, Guy. Bye bye, everyone.
Bye bye. See you, everyone.